Awesome, thanks. Thanks very much, Christoph. And thanks everyone for being here. I'm in San Francisco at the moment, so for me it's 7 a.m. in the morning, bright and early on the weekend. So you'll have to forgive me if I'm slower in the first half. And maybe I'd recommend, if there are particularly tough questions, you can strategically leave them until some point later in the talk, and you'll probably get a better answer from me. So I guess the first thing, I'm going to make sure I can actually share my screen. And as Christoph said, I'm going to be talking about fault-tolerant quantum architectures. And so this is, I guess, the topic that I think about every day, and in particular in the context of working on that for photonic architectures, which is the work that we're doing at PsiQuantum. But I'm really going to talk about this kind of in a much broader sense. And I think this is a particularly kind of exciting time for this field. There's a ton of stuff going on. There are loads of talks coming up during QIP that are kind of on all different aspects of this. And one of the things that is kind of nice about this topic, quantum architectures for quantum computing, is the kind of breadth of how it spans across all these different areas of physics, from the very theoretical to, you know, real engineering work in trying to turn these ideas into reality. And I'm particularly going to be talking about topological error correction as a basis for these quantum architectures. And so there's kind of this whole trajectory of different fields that are related to this. So, you know, at the one end, you know, we have these topological quantum field theories where, you know, we have particles behaving in some way in some space. You know, we can braid particles and see a certain behavior. These are condensed matter systems. And in a sense, this is sort of the inspiration or the underlying physics that then leads to the construction of topological error correcting codes, which, you know, are a more specific method, but that uses those principles to design techniques for tolerating errors. And, you know, here we can look at all these ideas of how we can build these codes, how we can turn them into gates. But, you know, there's still kind of a level of abstraction there. And then the next stage in this process is in kind of taking a step towards reality, is to understand how those things can actually be built in a, you know, out of physical primitives, out of real components that, that you can actually get access to from physics. And this is what I'll call a quantum architecture. So maybe if I just scroll down and kind of look at a few words describing these different things, you know, quantum architecture is still one step removed from reality, but really starting to inject some greater level of that into the system. And then, of course, you know, this story doesn't end there. It continues into even more physical systems. So, you know, let's call it a system architecture, where we actually start to think about devices, you know, where is power coming from? How are we getting heat out of the system? How is the thing getting, you know, actually packaged up together so that it's going to work? And so, you know, this is the story from like sort of the most theoretical side to the most practical side of the pieces that go into building a quantum computer. And error correction is really at the center of all of that, because qubits are so notoriously noisy and problematic and suffer from errors. And obviously the end goal of this is to be able to perform a useful quantum algorithm. And, you know, as things stand at the moment, that's something that requires running billions of quantum gates. And so it's just really necessary to have error correction be at the center of this. And so this is the kind of the story that I want to talk about. And actually, what I'm going to talk about here is focusing on these two pieces in the middle. So I want to start by looking at these topological quantum codes and kind of setting up the framework for what those things look like, how we can construct them, and how we can use them to do error-corrected logic. And then I want to look at kind of this transition. How can we start with these, you know, these theoretical models of error correction that, you know, have description of quantum states, maybe some toy error models, and translate those into a model where we're kind of constrained by all of the actual effects of reality. So, you know, time and space, and how do things actually connect together, and what are the physical operations that the physical system is actually going to allow me to do. And so I guess, you know, it may look, you know, in this way that I've drawn this, that this is sort of a one-way trajectory. So we kind of start off with some abstract theory, and then we work at adding subsequent levels of reality to it as we go through. But I think, you know, really the reason to do this, the reason to look into a quantum architecture and understand the implications that that has, is just as much because this, you know, this direction really goes the other way by taking a theory, putting reality into it, trying to understand how that affects the system. That can then teach us something about the theory that we're using, and we can take that back and use it to, you know, add depth and to expand those theories or improve them in a way that's going to allow us to then, you know, go through this cycle again and improve our quantum architectures. So this is the idea, and you know, roughly speaking, I'm going to kind of be starting with these codes and then moving on to quantum architectures. So let me just look at the brief outline. So just a kind of little bit of a summary before we get into any actual stuff. And I think it's helpful to look at this kind of a picture that I have here, which is what you might call the stack of a quantum computer. And, you know, the task that we're looking at, quantum architectures, is this very broad topic that spans all the way, you know, all the way through these different levels of abstraction. And then at the physical level, sort of all the way through these different length scales. So, you know, you kind of often see these pictures of the layers of a quantum computer where you're starting at the smallest levels. So how do you encode a qubit? And then building up through these layers of operations. How do you do gates? How do you assemble those gates into kind of small circuits that are going to be building blocks for your computation? How do you compile those things into some scheme for error correction? There's maybe some classical processing elements and decoding, and then eventually you end up kind of where you want to get to, which is the ability to execute logical gates. And I put this thing here because it's kind of helpful to try and keep the whole picture in mind as much as possible, even though we're going to dive in on a whole bunch of the details along the way. And so the approach that I'm going to take here is, this is, you know, 2 90-minute sessions. So we've got 3 hours in total. And for the first part, we're going to focus on this end of that stack. So trying to understand, what is error correction? How do we build that up to get from kind of a starting point of noisy qubits all the way through to being able to implement error-corrected, fault-tolerant logical gates? And kind of roughly speaking, I'm gonna start off by just introducing error correction kind of in itself, and I'm going to look at this example of the surface code. And then move on to how you can use that as a basis to do the thing we really want, which is fault-tolerant quantum logic. And then in the second part, so you know, there's going to be a half-an-hour break and then another 90 minutes. And in that part, we're going to go back to this lower stage of the stack and really try and understand, when we start with a physical system which has some actual operations that you can do and maybe has a whole bunch of constraints, how do we go from there to, you know, connecting to this theory? So this is the idea. I'm going to do a particular example, which is kind of looking at how that works with photonic qubits, and I'll talk through a few other examples as well. Also, just a comment, in all of these slides, there are often these notes at the top, which is just because, you know, if someone's internet connection cuts out, or maybe if my internet connection drops out and you miss something, then they're kind of a summary. You don't need to read them. They're just there as a sort of reference point. Everything I'll be saying or writing it down somewhere else. I guess, yeah, one other thing just to mention is on the questions. I think there's a Slack channel and you should write questions throughout. I'll pause at a few different points to stop for questions or maybe just to take a quick break. And Christoph is going to be kind of reading those out to me at a few different points throughout the thing. Okay, so let's jump in. And I think just before I really get into quantum error correction, there's one principle that I want to start by kind of putting here right up the front. So it's kind of, it's going to come up over and over again throughout the course of these talks, which is that when we're thinking about a quantum architecture, you know, we're often kind of down in some of the microscopic details or looking at some error correcting code, but it's really very, very helpful as we're going through this process to try and keep in mind as much of the quantum computation as we can. So ultimately, when we look at all these systems, when we look at error correcting codes or, you know, schemes for designing quantum circuits to do some kind of operations, these things are part of a process that it is aiming to build up a whole quantum algorithm, a fault tolerant quantum algorithm. And that's really the goal. We want a quantum computer that can run billions of error-corrected logical gates so that we can solve a useful problem that people care about. And so it is going to be very helpful to us as we're doing this to try and think about not just a time slice, not just qubits, but the whole world line of the quantum computation or of the system that we're looking at. So I'm just putting this up here at the front. It's going to come up over and over again throughout the whole course of this. And hopefully by the end, I'll have convinced you that this is like a valuable perspective to take on this whole system. Okay, so now we can get into some actual things. So we're going to start by looking at just quantum codes. So this is kind of starting off as a kind of an introduction to some kind of standard material, just looking at what quantum codes are, and then we're going to build up to how we can use that to do fault tolerant logic. And so the idea of the quantum code is, if forgetting error correction for a moment, we have qubits. So we can have some unencoded qubit, which we, this is our qubit and it has some quantum state psi. And this qubit has a bunch of properties that we can use to describe the way it behaves. This qubit we can think of as being, some component of this algorithm that we want to run. So what properties does it have? Well, it has some logical operators. So these are, operators that can manipulate the quantum state that we can use to move around within the block sphere of that qubit. So, for example, if I take the X operator and I act on the state 0, I get 1. So another property that you have is that these operators have a particular algebra. So they relate to each other in a certain way. So if we want to just try and describe this qubit by its operators only, and sort of, forgetting about the state, we can see that those operators have a particular relationship. And there are a few different things that go into this, but the one that is kind of particularly relevant for this is that the X and Z operators anti-commute. And this, means that they have this relationship that XZ equals minus ZX. So if you swap their order, then you get this minus sign at the top. Okay, what other properties do we have? Well, redundancy, there is none in this case. And this is really the point, which is this qubit has no redundancy. There is no redundancy in the logical operators. And so if there's any kind of error, then it's going to lead to, something which is uncorrectable. And we're thinking about some kind of physical qubit that has, that is trying to ultimately represent some real qubit. So it's also something which has some physical error rate associated with it. Okay, so this is our unencoded qubit. It has a bunch of properties. And the goal of quantum error correction is that we want to take that qubit and instead of just having one qubit, encode it into a system of many qubits in such a way that we add redundancy. And ultimately, the goal of this is really sort of starting at this point at the bottom, which is that we want to be able to have a qubit that has an error rate that is, let's say 10 to the minus 10. I just throw that out there for the sake of argument, but where does this number come from? If we want to run a quantum algorithm with 1 billion gates, and every one of those gates has some probability, p prime of failing, then roughly speaking, we want the overall error rate to be less than 1 over the total number of gates, so that over the course of a whole quantum algorithm, we have a good chance of getting out a meaningful answer. So this is the goal, and the way that this quantum code kind of achieves that is by adding some redundancy to the definition of that qubit. So somehow in this collection of qubits, up here, we qubit in some subspace of that collection of many qubits in a way that allows us to protect it from errors. And so a helpful way to sort of think about the definition of this qubit is to go to these operators that describe the qubit, and think about how they translate across. So in my encoded qubit, I'm going to have logical operators. I'm going to call those X bar and Z bar to indicate that they're the operators of this encoded logical qubit. And these just are defined in the same way. So they have an action on the logical state, again, using bar notation to indicate the logical state that is the same as the unencoded qubit. Then the algebra of the operators needs to be the same. So these operators also need to have the right relationship to each other. So we should find that these operators also anti-commute. And then the key part really is here, which is that in our encoded qubit, there should be redundancy. And this is kind of the whole point. We want to design the system with logical operators in such a way that those logical operators are redundant. And so that is the goal. And then I guess just briefly to say, I'm starting off by talking about quantum codes because it's kind of a helpful way to build up to where we want to get to. But again, to this principle of kind of thinking bigger to what we ultimately want, a quantum code on its own is not enough. A quantum code is kind of a static object, right? If we just think about it, it's a collection of qubits that has a state in it. And we can often just think about that as being a memory for logical information. So it's just a sort of this static object. What we really want is not just a memory, but the ability to do logic. So we want to be able to implement it's not really static anymore. We're looking at a dynamic system where we can, maybe based on this quantum code, implement fault-tolerant operations or a fault-tolerant channel. So that's really the point that we're trying to get to. But to get to that point, it is really helpful to start with quantum codes. And so I'm going to talk about these codes with the example of the surface code. And the reason to do this is that it is kind of by far the most widely studied and pursued as the most likely code that will be in the first generation of quantum computers. There's a bunch of reasons for that. So it's has a particularly high threshold against errors, so it can tolerate a lot of imperfections. And it's pretty practical because of the fact that you can really embed it into 2 dimensions. So if you're constrained to operating in some 2-dimensional system, then it's easy or possible to engineer the interactions that you need to create this kind of a system. Okay, so let me look into this example then, which is now kind of specific case of this general thing I was talking about before. So we have some qubit, and we're going to encode it into a system of many qubits. And so in this picture, there's a qubit on every edge of this grid. So every one of these edges is a qubit. And I'm not going to draw all of them. There's a whole lot of qubits, but you can see we have this big sort of square array. Now, the next thing we want is to see where our logical operators are. And so I'm just going to define those logical operators. And so the first one is our Z logical operator. And we're going to define that to be a string of Pauli Z operators acting on qubits that go down a line of these edges from the top to the bottom of this collection of qubits. So that means I have an operator that is the tensor product of these Z operators on this set of qubits and then identity everywhere else. So that's our Z logical operator. And then we can define our X logical operator in quite a similar way, except it's going to just be configured slightly differently. So our X logical operator is going to be an Pauli X operator on every qubit across a row, going from left to right. Okay, so I mean, I've just stated that these are logical operators, but we can check that they're kind of an appropriate choice of operators by looking at if they have this anti-commutation relationship that we know we need to have. And we can see by looking at these two operators that they are going to have that relationship. And so you can kind of see that if I take my Z operator, all of these terms that are sort of up here, they overlap with an identity in the X operator. And so those two terms are going to commute. Then all of these X terms, they also overlap with an identity. And there's only one site, which is this one right in the middle, where the two operators actually overlap in a non-trivial way. And since the physical X and Z operators anti-commute, that means that our logical operators are also going to anti-commute. So we can kind of like check that off. Yes, these operators have the right commutation relationship and that they anti-commute. So, okay, that's all good. But by looking at the system, you can see that actually this Z operator that I've drawn is not the only operator that would have that property. And in fact, you know, if I were to look at another variant of this operator that was going down this row, then this would also have the same property, would also anti-commute. And so this is now giving me some alternative representation of the Z operator. Maybe I'll just comment in case it's very confusing. I'm English, and so I'm saying a mixture of Z and Z as I go through these, but you should know that those are the same thing, and I'm going to try and be consistent. Okay, so we have these two different representations, and actually, you know, I'm going to stop writing all of the little Z's down and instead just color the edges in. But I could actually take any kind of string of these Z operators that goes from top to bottom. So I can take one like this. This also overlaps with my X operator at only one location. And so they also anti-commute, you know, and this thing doesn't have to follow anything like a straight line. Like it can go in some kind of wiggly route, and it also overlaps at one location. And so you can see there's this whole set of different logical operators that are all having these right properties. And so we can see that we have this system that has redundancy. So I have many, many possible representations of this logical Z operator. And the same thing is going to be true for the X operator. So it's also the case that I don't have to choose just this representation of X. I could start, I could have some operator that goes down a different line. Again, I can see this thing always is intersecting with my Z's in one location. And again, like the thing could go in some kind of wiggly route, and again, it would always follow the same thing. So there's one thing that that is just, I put into the definition of the X logical operator that maybe is just worth commenting on, which is that you'll notice when I'm drawing these Z operators, I'm putting the Z's on these lines that are the lines of the grid, whereas the lines of the X operator are sort of going perpendicular to the lines of the grid. They're what you might call the dual edges of the lattice. And the reason for that is just it's the part of the definition that is needed so that you correctly get this anti-commutation relationship. So you can play around with this example and check that if you were to define the X's to go on the lines, then you wouldn't end up with the right relationship. But if you define it in this way, then everything works out. Okay, so this is our system. We have a whole bunch of qubits. We have a whole set of different Z logical operators and a whole set of different X logical operators. And okay, yeah, here is this reference for this, which ended up being cut off the bottom of the page. This is the original work by Kitaev, where he introduced this system. It's really kind of the foundation of all of this work that has been done on topological codes that's followed. Okay, so we can now just kind of zoom out and see that we have a system where we have any sort of string of Z's that is going from top to bottom is going to be a Z logical operator. And then any string of X's that is going from left to right is going to be an X logical operator. And I think, you can already see when we look at it like this, the topological nature of this code. So I don't care about like the exact formation of these operators, and they could really have any configuration. The only thing that is fixed about these things is that they're non-trivial. So they span this grid, either from left to right or from top to bottom. And everything that happens in the middle, the actual shape of those things could be deformed in any way. And so, this is why this thing is a topological code, because these logical operators are encoded in these, topologically non-trivial cycles. So this is really the definition of these logical operators, which is that they're these topologically non-trivial objects. Okay, so now we have a system, we have these redundant logical operators, and this actually defines our code. So the definition that we have now is actually enough to define that code. But often it's the case that just looking at these logical operators, like, maybe I've got like thousands of different representations of the logical operator, which give me redundancy, is actually not a very helpful way to understand the redundancy. And so this is where the stabilizers of the code come in, which is something you've probably always heard associated with quantum codes, and it's kind of very common to use this as a framework for understanding their behavior. And so, okay, to look at this, it's helpful to go back to thinking about these operators of a qubit. So let's say our Z operator acting on our unencoded qubit. So there's another property of this operator that we didn't talk about yet, which is that a Pauli operator, when I square it, so if I take the product of it with itself, it gives me the identity. So these operators are unitary. And we should like we should expect that with our encoded version, so with our Z bar, this is going to have the same behavior because I'm kind of encoding that state. And maybe I say like another way of writing this is that, you know, Z squared acting on the state gives us the state back. So this is kind of the thing that we're expecting to see. And so if I look at my one of my Z operators, so let's just take the string of Z's. I won't keep writing out all the Z's, but I take the string of Z's that goes from top to bottom here. And then I square that operator. So I take the product of it with itself. Then, yeah, I can see that this thing is going to indeed square to be identity, because at every site I have applied, you know, now 2 Pauli Z operators and they have cancelled out. But on the other hand, I now have many possible representations of this logical operator. And if I instead were to take, say, this string, let's call this like representation 1 of our Z logical, and another string that follows some different route, let's call this one Z2. So these are 2 representations of a logical operator. It's now the case that when I take the product of those 2 things, they do not square to give the identity. And so, you know, it seems like, you know, we're not actually achieving this property. If I take Z1, Z2 logical, then I get something else that is not the identity. And so this is really where the stabilizers come in. And it's from looking at this, you know, if we look at this expression, what we're actually trying to achieve here is that if I take the square of one of these logical operators, its action on the qubit is trivial. And in my encoded qubit case, if I take 2 logical operators and I apply them to the encoded state, I know that I should be getting back the encoded state again. And this is exactly the definition of what the stabilizers are. So if I take the product of any 2 logicals, I know it should have a trivial action on the state. In this case here, I can look at these 2 logicals and what does the operator look like? Well, you know, up here, everything sort of cancels, and down here, everything cancels out. But this region in the middle, I'm left with a sort of string of Z operators that goes around a loop. So this thing is sort of a ring of Z's. And because of this definition, what I can see is that this thing, which I'll call S, this thing has to have a trivial action on the state. So S psi equals psi. And this is what we call a stabilizer. So the stabilizer is this operator, which when you act it on the code space, it gives you back the same code. And another way of thinking of that is that this is the encoded identity operation. And it's a feature of the fact that you have many, many logical operators with this redundancy in, that there are actually many, many of these operators. And we can look at a different example. So if we have, you know, some logical operator like this, and we take the product of, you know, some other one, then we're going to be left with some other loop of these Z operators. And you can go through a bunch of examples, and what you kind of see is that it's always the case that these things form loops. And I guess the other thing to say is that these operators then form a group. So it's really helpful, I think, to think about the stabilizers as a representation of the redundancy of the logical operators. These are the operators that you can apply that sort of move you between the different representations of the logicals. They form a group, and that group is generated by these kind of the smallest possible loops, which are these plaquette operators, often called plaquette operators. The things that belong, so a Z on the four edges of a square. And so, you know, the reason that the code is redundant is that we have these many different representations of the logical operators, but these stabilizers really give us a kind of much more convenient way of describing it. And when we start to look at actually using this code, trying to deal with all these logical operators becomes completely unwieldy, and using these stabilizer generators gives us a compact way of looking at what is actually happening. Okay. So Christoph, maybe I want to just pause there and see if there are like one or two questions to go through now.
Sure. So there was already a bunch of questions, but people in the Slack channel also like jumped in and answered most of them. But maybe you can comment on, there was one question about the difference between toric code and surface code, and question about like how about higher dimensional version of this. Maybe you can comment on that.
Yeah. So okay, so on the surface code versus the toric code. So I'm using surface code, I guess, in a broad sense, in a way that encompasses the toric code and things on different geometries. So if I look at this system that I've been looking at, and you just kind of think at some patch of this, where I haven't defined any boundaries, this is, I guess, something which is, you know, the definition of the surface code, what is happening in here. And the version that I've kind of drawn out here has boundaries. So like it ends at some point, and there's some kind of features at the edge that have terminated the logical operators. And this is what is often called the planar code version of the surface code. But there's an alternative thing which I could do, which is rather than kind of ending the surface here, I could kind of connect this thing back to the top again. And then I could connect the right side around to the left side, so that the thing becomes, is sort of wrapped around a torus. So, and that's what is called the toric code. So I guess, you know, there are other topologies that you can use as well. Like you could have some kind of donut shape that has multiple holes in, and this would, you know, have some different number of qubits encoded in it. But the kind of the fundamental behavior of these things is all the same. And kind of, yeah, all of these properties are the same apart from the way that the boundaries are behaving. Then on higher dimensional codes, I might defer that one until later. So we're going to kind of look in a bunch of detail at the 3D structure that you need to get to fault tolerance, like on top of this 2D code. And yeah, I can talk a little bit about some actual higher dimensional codes themselves later on. Okay.
Maybe another one.
Yeah.
So someone asked about, what about like the operators that are not logical and not stabilizers? What about them?
Yeah, so I think the next thing is going to answer that. So if you have a Z operator that is not a stabilizer and not a logical operator, then that's the kind of thing that we can identify as an error in the system, something that we sort of didn't want to happen. And so those are gonna turn up straight after this. Okay. I think I'll go into the next section, and then we'll pause again and after a little bit to answer some more. Okay. So now we've sort of defined this code, and we have these logical operators, we have these stabilizer operators, which give us a kind of nice way of seeing what the redundancy is. And now we want to look at, like, how do we actually use that system in practice if we want to do some fault tolerant operation? And so the example I want to look at is that someone sort of gives us some encoded logical state psi, and we want to measure the logical X operator. That's the goal. But while we get this state, it's kind of we have this perfect logical state, but it has gone and accumulated some set of Pauli errors. So what I mean by that, like this is often use this phrase Pauli errors, or use this as a model of the kind of things that can go wrong, which is that a bunch of the qubits have some operator applied to them. And so, you often use a model, which is that with some probability P, you apply a Pauli Z operator to the qubits. So every qubit has some probability P of having a Z operator applied. And so let's say that, we have some set of these qubits, which have randomly had some Z flip applied. And what we want to do is measure the X logical operator. Okay, so what is the effect of those Z operators? Just to kind of like zoom in on what is going to happen. If I measure one qubit, if I measure it in X, so if I make an X measurement on a qubit that has suffered a Z error, these two things anti-commute. And so the effect is going to be that when I make that measurement and I get some outcome, which is 0 or 1, if the outcome should have been 0 if there were no errors, it will be flipped so that I get 1 because this thing anti-commuted. So anywhere where there's some Pauli Z has happened and I make a measurement that has an X term on that qubit, then the measurement outcome is going to have its value flipped. So we're going to get kind of an error in the outcome. And so, our goal here is to measure this logical operator. And so, okay, so we know we have lots of different ways of measuring that operator. And so, maybe one thing we could do is to make this measurement of X's, and we could measure all of those qubits in the X basis. But what we can see is like, this is the problem with these errors, which is that they anti-commute with some of the logical operators. And so, if I were to measure this one, this logical operator, and just that, then I would get the wrong outcome. So that would give me an error. And so the way that we can use this system to do a fault tolerant measurement is to make use of the fact we actually have a whole ton of different representations of this logical operator. And so the procedure that we're going to follow is to measure all the qubits, and we're going to make single qubit measurements on all the qubits in X. So measure X on everything. And that is going to allow us to reconstruct every different possible combination of those logical operators. And what we should see is that we'd expect that like many of those representations give us like some outcome. Some of them will kind of be giving us an error, but we now have some system where we can try and deduce which of those outcomes are right. Some, a majority voting thing is a kind of example. Like if we have a ton of different representations of the logical operator, what do we actually think is right in the end? But again, this is really the reason to use these stabilizers, which is that you can see that if I just try and write down like my thousands of logical operators and evaluate them all, it's a really messy system. It's very hard to kind of understand what has happened. But what is much more, what is a much easier thing to do is to instead look at the stabilizers of this system and evaluate those. And so the stabilizers here, and I guess maybe I should mention this, the stabilizers that are X type look like this. So rather than being, our Z stabilizers look like these little plaquettes. And these X operators are, very similar, but they're kind of shifted by, half a lattice site onto be centered around the vertices. Those things sometimes get called star operators just because they're sort of like centered on these crosses. And because these things are a stabilizer, what that means is that when I take the product of those, these 4 measurement outcomes, I know that should have a trivial action on the logical state. And so I expect that this thing should give me an even parity outcome. It's saying that the operator has a trivial action on the logical state. And so if I measure that operator, then I should get an even parity outcome. Okay, so then we can look at our system, which is not perfect. This is what happens, if everything is perfect. But when these errors have happened, then this property is sometimes going to be messed up. And so we can kind of look at an example. So I can, let's say I look at these 4 operators here. Well, this is all good. Like these things, there's no Z errors present. And so, I'm going to see an even parity outcome. But if I go one site over, and instead I look at making an X measurement on these 4 sites, now I have one location where there's a Z operator and an X operator that anti-commute. And so when I make this, what that means is that when this particular measurement got flipped, and so when I evaluate that stabilizer, that check, I'm going to instead see an odd parity outcome. And so the same thing is going to happen anywhere where I have an odd number of these anti-commutations happening inside those stabilizers. So I guess you can kind of see there's going to be another one that happens here. So if I measure these 4 X's, then these are going to anti-commute with this Z. In fact, what happens in the middle, so if I look at this site, then, and I measure this operator, it anti-commutes twice, and that means overall it actually commutes. And so here we don't see anything. This thing will give an even parity, but this one at the end, will give an odd parity. Okay, and we can kind of continue this process. We can look all the way across this whole grid and evaluate all of these stabilizer operators to try and get an understanding of what is going on with that code. And at this point, I want to kind of introduce a slightly different representation of this system, which is really helpful to try and interpret all of this information that has gone on. So, we've got these qubits, they've suffered errors, we've made a bunch of measurements in the X basis, a bunch of those had errors, and now we've sort of tried to evaluate all of these parity checks, these stabilizer operators, to identify the locations of errors, and to try and get a grasp on what is going on in that system. It's really helpful to move to this representation of the syndrome graph. So the syndrome graph, and you can kind of see visually from this picture, looks very similar to that previous one. It is a representation of the classical correlations that are left after we've made these measurements. And it describes the behavior of the errors. So before we were kind of looking at a whole bunch of qubits. And in this system, like, we should forget the qubits. So there are no qubits anymore. And instead, we have a system where our vertices, so every vertex here, this is now, a graph with edges and vertices. The vertices represent the parity checks. So, there are kind of these 4 measurements going into every one of these parity checks of these X-type stabilizers. And the edges, well, they represent the locations that errors could happen. And here, those errors were these errors on the qubits, but actually in general, it's kind of more helpful to think of these things as just being any error that could happen in the system. And when we look in this picture and you kind of evaluate those parities, it's the case that in most places, those vertices, they have an assigned value after we've evaluated them. And in most places, those things have an even value. Here I'm representing the errors that have happened. So these, these Z errors by these black edges. So these are errors. And in this picture, it's then kind of very easy to see what happens, which is that we see these odd valued checks at the ends of chains of errors. And so this picture, I mean, it's describing exactly the same thing that we were looking at here. We're evaluating parity checks and it's showing the locations of errors. And obviously that is a particularly messy drawing that I've done of that system. But the syndrome graph gives us this really clean representation, which sort of keeps the right level of information. So it keeps the relevant information about the system that we need to try and analyze it and then understand what's going on. And it's kind of particularly useful because it's going to be very helpful for thinking about solving the decoding problem. So trying to run some interpretation of what we think has happened here. And it's also helpful because it is this kind of central tool that then we're going to be able to translate across many different possible platforms. So regardless of what kind of physical system we're using, this is kind of the centerpiece that we can use to understand the actual underlying structure of the code. Okay, so I'm going to come back to this syndrome graph over and over again. Maybe one thing I didn't say is why do we call it the syndrome graph? And that's because this kind of collection of locations where there is an odd check, that's described as the syndrome. So, as someone running this experiment, we got a code, we made a bunch of measurements, and what we see are these locations where these parities were flipped. And that's referred to as the syndrome of a particular instance of running this code. Okay, so let's go on to decoding. And so I'm going to talk about this for sort of a few more minutes, and then we can go on to a few more questions. And so decoding is we're now at the part of the process where we need to do some classical processing. So we have this system, we've got qubits, there were errors, we made measurements, and we've kind of assigned those on our syndrome graph. But the thing that was sort of unfair about this is that actually, if we are the person who's doing this thing, or, our quantum computer is doing this in practice, we do not get access to that knowledge about where the errors are. So, that was kind of helpful. We were thinking about what has happened, that was like us simulating the system. In reality, you only see these endpoints. So the only thing you see are these locations where there's this odd parity check. And so the job of the decoder is to look at this system and try and kind of estimate what happened. So that is the goal, is, we see this thing, well, what probably went wrong and what can I do to correct it? And so in some cases, if we zoom in on this place and if you were trying to decode this by hand, you'd probably make the pretty good guess that, well, probably there was a Z error here, there's nothing else has gone wrong anywhere nearby. It seems very likely that, there was one error and that's what caused these two things to flip. But, if you look at this one, that's a little bit harder because, well, okay, well, maybe it was this, but, maybe it was that error chain that caused those two things to turn up. And let's say we guessed that it was this one. That seems like an equally good guess. I mean, these two things are equally likely. But the actual thing that happened was something else. And so, this can happen during the decoding process, which the guess is not the same as what actually happened. And so, if we think about, this one, we guess that there's a single error connecting the two things, and that is indeed what actually happened. And so if we kind of cancel out our correction with what happened, you know, we successfully identified the actual error. There's nothing left over at the end. In this case, we guess something a bit different. And if you think about kind of the error and then us going and maybe trying to apply our correction and thinking about what is left behind, is a sort of loop. That is the difference between those two guesses. And so this is really one of the critical things about decoding, is that this is totally fine. So this is a successful correction. And the reason for that is that this thing that is left behind, that is a stabilizer. So this is one of these loops that were these stabilizer operators. And remember that our stabilizer operators are basically the logical identity. And so when we're doing this decoding, it's only necessary to correct it up to these stabilizers. You know, and in fact, you could have a situation where I guessed that these two were to be connected. You know, I guessed that these two should be connected, and in fact, it was actually this is also something that, because the thing that is left behind afterwards is a loop. And so, you know, that's really the decoding problem, which is look at all of these syndromes, look at all the locations of the odd parities, and try and make the best guess at what happened up to these stabilizers. And now, you know, this process does not always work. So there's a lot of ways in which, you know, you can be successful at doing the decoding, as long as you're only leaving these loops behind. The time when it fails is if, let's say I made a guess that, and what actually happened, of course, is that there was this error in the middle. And now the total effect of that is to have introduced a logical operator. And so that's when you fail. You succeed if what you introduce after decoding are just these little loops, and you fail if you introduce something which is topologically non-trivial. And now, yeah, I could talk easily have filled 3 hours just talking about decoding. You know, this is a whole field of research, which is designing methods, so, you know, algorithms to try and solve this problem as well as possible. And, you know, in general, it's a very hard problem to get the exact answer, you know, the exact, you know, best possible guess at what happened. But there are, you know, a whole bunch of efficient algorithms that will do a pretty good job. And there's a ton of stuff that can be done of like really trying to optimize those schemes to do as well as possible. Now, so I'm not going to talk about it much more, but I just wanted to show this. Oh, did I stop sharing? Okay, let me take another attempt at that. So yeah, I have this little GIF to show of just the decoding process. And I guess the thing to sort of understand about that is it's an algorithm. And the syndrome graph, again, just to come back to that, like this is one of the key reasons why this is so useful, that the syndrome graph describes, I wonder if this GIF is what crashed the thing from sharing. Oh, it seems like it is. How interesting. Okay. Well, I'm afraid you're going to have to miss out on that nice picture then, but I'll just I'll tell you in words about what that is doing while I'm trying to get this there again.
Maybe you can put it later on the Slack.
I'll post it on the Slack channel for you all. But so the idea is that you have some graph structure, and really like what the decoder is doing is some kind of graph algorithm of interpreting, you know, what has gone on, and kind of manipulating the information on the graph to get some guess at what has happened. So I'll post that in between and talk about it. And now I don't want to go back there in case it's going to make the thing crash again. the one other thing I guess I wanted to talk about is, you know, how do you quantify how well your decoder is doing or how well your code is doing? And so the decoder, when it interprets the system, sometimes succeeds and sometimes fails. And what we want is for it to succeed most, you know, as high a proportion of the time as possible. And so the way you can kind of study this is by looking at our physical error rate, which is, you know, how often were those errors actually occurring on the underlying system, versus the logical error rate. So how often are we ending up with these errors after we've done our whole encoding process and decoding? And what you'll find is, like, we can look at this for our system, and if the physical error rate is very small, then our logical error rate is going to be really suppressed. So, you know, maybe we end up with like a 10 to the -6 probability of logical error if our physical rate is, I don't know, you know, 1%, as an example. But as the error rate increases, you can see that you're going to end up with a higher and higher density of these syndromes, and the decoding problem becomes harder and harder. And so this thing sort of increases, and actually the way it behaves is that it goes through a transition. And so there is some kind of threshold here. So the thing shows a threshold behavior. It's kind of really related to like percolation type thresholds that you might have seen in other contexts. And you know, the effect is, if I had a system of infinite size, then it would just have a sort of step function here. If I have a small system, it's sort of going to be shallower, but there's this crossing point, and if you're below this, then, you know, here I can correct. And if I'm above it, then, you know, it's a no-go. There's nothing you can do. If I make my system bigger, I just end up making things worse. And so this threshold is really a measure of how much physical error rate on the qubits can you tolerate, sort of in theory. And I guess the one other thing to say about this, just to kind of take a step back from this example, like I looked at this one example of this square surface code, but surface codes are actually kind of a broader class than that, and they can have many possible geometries. So I could define a very similar system on, you know, I just took this picture from Wikipedia of the Archimedean lattices, but, you know, you can define many possible tilings of a surface, put qubits on the edges, and define my logical operators as these paths, and they would all have the same property. And if I choose a different geometry, then it's going to have a different tolerance to error. And so this is kind of another reason for looking at the syndrome graph, which is the syndrome graph can actually tell us a lot of things about the system. And so even, you know, we use it for decoding and kind of doing analysis, but actually even just looking at the structure of the syndrome graph itself can tell us something about how much error we're likely to be able to tolerate. And so that's kind of a very useful thing then when you're looking to try and design codes that are going to behave better and that are going to tolerate more error. And so, you know, specifically, and this is a slightly different example of error, where if we look at erasure, which is a type of error where you know its location. So it's like something goes missing and you know about it. It ends up being quite closely related to the way that Pauli errors behave. So it's still kind of useful. But for this kind of error, and you know, this is actually also for a three-dimensional system, the syndrome graph valence, so the connectivity of the syndrome graph, actually predicts very precisely what the threshold is going to be. So, you know, it has some kind of behavior where I can predict the threshold based on properties of this syndrome graph. And so I guess this kind of puts it in context. Like the syndrome graph is really, it's a description of the system. It describes the way the errors behave. We can use it for decoding, but also just it in itself and the structure and the geometry of that thing is useful information to try and understand some of the behaviors of the code. So I think, yeah, I'm going to take a break there to see if there are any questions. Yeah, maybe we can take a few, or if people need to go and grab a quick cup of morning coffee, if you're also on the West Coast of the US, then maybe we can take, 3 or 4 minutes of questions, Christoph, before we go on to the next part.
Yeah, so you have some questions about thresholds. Mm-hmm. So, for example, does the threshold graph take into account that error can increase with system size?
Okay, yeah, so that's a great question. And that's something which is, of course, critically important when we're thinking about quantum architectures for real. So the way I've drawn it, it doesn't. So the threshold graph can take account of that. And that's really a feature, not of the graph, but of the error model. And so here, like the error model that I've been looking at is the sort of simplest possible thing, which is that we had IID error, that's like independent and identically distributed error. And I only had like Z flips as well on all the qubits. And so this is like very much a toy error model that is useful for understanding sort of the fundamental behaviors of codes, but it has really no relation to reality. And when you start to move from these sort of toy systems through these layers of adding kind of reality into the system, then yeah, you have to account for things like that. And it's very dependent on the system, of course, like the way that the errors behave. Like if the errors are going to increase the system, that's something which is like very deeply tied to some of the physical properties of the actual qubits that you're using. So yeah, maybe I can try and talk to that a bit more in the next half when we start to get more into kind of the physical architecture.
Then another one is, does the threshold depend on how fast you can decode and correct errors?
Does the threshold depend on how fast you can decode? This is a great question. And the answer is no. The threshold does not depend on how fast you can decode. And that is because, and this is sort of something which has certainly not come across from what I've presented so far, in practice, you don't need to actually physically correct anything. And actually, it's kind of implicit in this example is you think about what we're actually doing, which is that we made a bunch of measurements. What we have is classical information. And the corrections are actually corrections of these classical bits that we have measured. And so although it's kind of, it can be helpful to think about that as applying corrections to the qubits, in practice, the correction is kind of keeping track of some, classical frame of reference information that you update to make sure that you have a correct state of the world. And so there are two pieces that go into the fact that the decoder speed doesn't need to affect the threshold. The first is that, when do you actually need that information? I only need the information from the decoder when I'm going to implement some kind of non-trivial logic gate. So I don't need the decoder to kind of just keep on executing an identity operation. If I'm just sort of doing, neutral operations, I can carry on doing that. And so it is possible to kind of make your system wait until you get a decoding outcome in order to go and do that non-trivial logic. And so it's a great question because it's totally critical, which is that the threshold does not need to depend on your decoding speed. Now, I guess if you were to link that back to the last question, which is if your threshold were dependent on the system size, that might not be true. So maybe if you have some kind of more complex error model, that could happen. But generally speaking, that is not the case. On the other hand, it is, of course, really important to have a fast decoder, because if you have a slow decoder, it's going to make your computation slow and bigger, and you're going to have to waste a lot of resources just waiting for your kind of classical computation to run.
Maybe a question about geometries. So do we have to try different surface code geometries to find the optimal geometry for the problem?
Yeah, so this is also an interesting question, and this I have linked here. This is something kind of looking into this question in 3 dimensions. So it actually turns out that in 2D, this square graph is really the optimal thing. But as we're going to see kind of shortly, actually in practice are operating with this 2D system when you're thinking about doing the computation. And in fact, you're always going to be having some different geometry. And so maybe I'm just going to kind of kick this question down the road slightly. I think there are 2 things, which is like that there is an exploration in that paper of looking at different geometries, dimensions, which again, under some error models can be really beneficial. And the second thing is that when we start to look at like real physical operations, the picture changes again. And so that is something else which can modify the geometry. And so we kind of need to tie all the things together. So I think I might move on to the next section so that we can make sure we have time before we go into the break. So, okay. And I think this kind of ties in nicely to some of those questions that you were asking. So thanks for that. And okay, the question really is, we've looked at this, set it up, we've kind of seen these fundamental properties of error correction. That's great, it's what we're after. But in the example that we looked at, what we did was measure the qubit, and we made single qubit measurements. And after that, we didn't have a logical qubit anymore. It was gone. We'd sort of measured it out. And so this is not good enough for actually doing computation. What we want to be able to do is kind of do logic and information alive. We want to be able to manipulate the state of the logical qubit without, destroying it. And so this kind of naturally leads us to thinking about a different picture, using this sort of space-time picture. As soon as we start thinking about what happens if we're trying to preserve the quantum information. And I guess I'll say specifically, there are different approaches to doing fault-tolerant logic. But I'm specifically wanting to look at this picture, which is fully topological. There are a bunch of reasons to do that. You kind of inherit a lot of this nice behavior of the locality of the operations and kind of being able to use the same tools. So to keep the information alive and keep the system topological, like we kind of immediately can think of a picture where, I have my, here's my logical operator at, in my code going into the system. And then at some point, later in the future, I want my logical operator to still be there. And, it's going to keep on existing at different points in time. And I can kind of look at this thing as just automatically producing the idea of a 3-dimensional object, where I now have this kind of membrane-like thing, which is representing the transformation of that logical operator over time. And so this is obviously still kind of a pretty abstract view of what's going on, but the transformation is simply that we started with a 2D code and we said we wanted it to carry on existing. And now we see that these strings became these membrane operators. We can also see that the things which were stabilizers, down here, it's a different color, these stabilizers, these things become some kind of like spherical closed membranes. And so this object is what I'm going to call a fault-tolerant channel. What is this thing? I'm sticking in a code, right? So some code is going in the bottom, and out the top is coming some other code. And in between is some description of what is happening to the logical information. And there are 2 things in there. So like there's there's like some description, these membranes, and that's describing sort of how is the logical qubit being transformed. And then there's these sort of now 3D stabilizers, which are representing that there's some redundancy in the system. Like it's representing that there's not just a redundancy in the logical operators, but there's a redundancy in the transformations being done to the logical operators. And, you know, my sort of bubble operators and these membranes, that the relationship there is sort of like exactly the same thing, which is I have one membrane that represents the transformation of some logical operator. And then I have another one, which, you know, maybe has some different structure. And then this stabilizer thing is sort of representing the transformations that can happen between these different membranes. And so, you know, this is really the thing that we're after. The code was a helpful starting point, and it showed us kind of a lot of the structure of the system that we're using. But the thing that we actually need, if we're going to use this to run a quantum, is we need to have a system like this that is, you know, we want it to be topological, and we need it to keep the quantum information alive as this thing is proceeding in a way that isn't itself fault tolerant. And okay, so that's what we're after. And this is the idea of the fault tolerant channel. Here's I guess the other logical membrane, this X type one, which is, you know, keeping your X operator alive. But okay, this is yes, this is good, but really, this is not enough. This version that I've drawn is kind of is doing something trivial, right? So at the moment, I'm just saying I want to be able to keep the quantum information alive. Of course, what I actually want is to be able to, you know, manipulate the quantum information. So I want to be able to do something like, you know, I put in some logical operator on the input, and on the output, I get some different logical operator. This is really, you know, what we want to be able to construct. We want to be able to kind of build up the system. So I put one thing in and I get something different out. And, you know, in the middle, or what is happening, well, something is happening there that's going to actually affect that change, so that there's some kind of system in the middle that's going to manipulate the way that logical information comes out. Okay, but okay, first I just want to just think about the simplest case, so the trivial case, and I think the reason for doing that will become clear. Because actually this really forms the basis of everything that we're doing. And I'm just going to put this picture here. So this system, now we've gone to a 3D system, but, you know, now we want to look at a slightly more detailed picture. And we end up with a syndrome graph. So kind of the same structure, the same idea, but now we're in 3D. And so, you know, again, now we come back to this definition and we see kind of how this thing is kind of going to be directly applicable in this new regime where we're now trying to look for these full fault tolerant objects, which is that the vertices are now these parity checks or stabilizers that are representing these sort of, you know, now these three-dimensional bubble type objects. And then the edges, well, they're also the same thing as before. They're representing errors that can happen in the system. And now I guess I'm going to talk a lot more in the next half about how you can really get to building up to these kind of things. And there's kind of a ton of stuff that goes into that. But just, I guess, to give you a sense, and one of the reasons that I'm focusing on the syndrome graph picture and kind of looking at, you know, how do we think about the channels, is that there are actually many, many possible ways to get out a set of, you know, measurement information or to build up a fault tolerant channel that has the same properties. And so, you know, the syndrome graph underpins everything. And just to give a few examples to kind of tie it back to something that's a bit more real, we could start with a 2D surface code, say made out of some kind of matter-based qubits, and make repeated rounds of measurement of those stabilizer operators. And that would build up this 3-dimensional block of measurement information over time. We have a code going in and coming out. And this is something that can kind of correspond to that system. But there are also many other ways of doing it. So another kind of approach would be, I could actually just build a 3-dimensional system of entanglement and then make single qubit measurements of it. And this could also be used to construct the same sort of fault tolerant channel. And so, this picture that we have in the middle is really kind of the underlying structure of what kind of correlations am I creating? What is the structure of the measurement information, and where is there redundancy in those measurements? And then, when it comes to the physical system, there are all these different ways of actually trying to get a hold of that information. Yeah, I guess just to kind of emphasize that, this is really something where, when you drill down into the details of how am I getting there from physical operations, there's a whole lot of complexity that emerges where you're trying to use, the real physics of the system that is underneath it, but they all end up in the same place, which is that you end up with, this syndrome graph with a similar structure. Okay. So let me just say a couple more things about actually doing the thing we want in the end, which is to be able to do non-trivial logic. So that picture was this kind of trivial case. We have a cubic syndrome graph that's doing this non-trivial thing. But of course, what we really want is this ability to be able to do something which is actually going to change the structure of the membrane as we kind of go through this channel. And so we're looking at a topological system, and the way that this manipulation happens is all about how we set up the boundary conditions of this system. So, I've been drawing these things that already have these boundaries, and someone asked this question about the toric code, which is the case where you kind of remove the boundaries and you set up periodic boundary conditions. But it's really the case that if I sort of had, a big chunk of bulk of the inside of this structure with no boundaries, I'd sort of have, membranes going everywhere in all directions. And so I think a helpful analogy of what is happening when we're defining these fault tolerant channels and setting them up to do something non-trivial to logic is to look at the principles of electromagnetism and waves. So I'm sure this is something everyone knows pretty well, or at least those from a physics background. If electromagnetic waves in free space, they can, I have every possible set of those waves of all different frequencies. Once you start to introduce boundary conditions into some area, I put a bunch of mirrors there, then you restrict which of those states can actually be there. Or there's, the simple example that everyone has probably studied in quantum mechanics, where if I create some bounding box, well for a particle, where I've put in the boundary conditions, I introduce a restriction into what states can possibly be there. And so, what you end up with is some kind of fixed set of those waves that are able to exist in this system. And this is all because of the way that you've introduced the boundary conditions and the effect that has on the state that can actually live on the inside. And the principle here is very much the same in our topological system. Of course, the setting is very different. There's a bunch of complexity and measurements that's gone into setting up this bulk. But by introducing boundary conditions in certain ways, you cut off which membranes can possibly exist in this region. And if I set those boundaries in a suitable way, I'm going to restrict it so that the membranes that exist are exactly the ones that describe the logical operation that I actually want to implement. And so, okay, you can look at an example, and actually, there's one we've already seen, which is the introduction of boundaries that sort of terminate the membrane. And, I guess the one that we already saw is that, you do not have one of the red membranes crossing in this direction. You only have it going in the other direction, and that's because your boundary conditions are set up in such a way to restrict the state. But we can also set up these things in a way to do something non-trivial. And one example with this kind of idea of converting one type of membrane into another is that you can introduce a defect. And okay, so there's a few references here that were to kind of a bunch of different examples about how these boundary conditions can get set up and used to manipulate quantum information. And so in this example, we, rather than like truncating the bulk by setting boundaries at the outside, we instead can change the boundary somehow inside the bulk in a way that, when this Z-type membrane passes through, it changes into an X-type membrane. And so we're doing something now non-trivial to that membrane inside that region. Now, physically speaking, there's a bunch of different ways of making this happen, but it could just be something like, at this time step, I'm going to perform a Hadamard gate on every qubit. So, physically, this is going to just turn into some set of instructions of operations that we can do. But at this zoomed out topological level, we can see this thing as setting boundary conditions to manipulate this quantum information in the way that we want to construct these fault tolerant. And yeah, I'm not going to go through this in example in detail, but just to kind of give a sense, so you can also construct these channels for multi-qubit operations. So I can have channels where I have 2 qubits going in and 2 qubits going out. And this one is just a sort of representation of a lattice surgery operation, which is a 2-qubit entangling measurement. And so, yeah, this is basically the end of this half. And I think we've kind of started from the basics of codes and come kind of full cycle all the way through to how we can build that up into doing these gates. And so I guess just to finish off, I just want to go back to this thing of the space-time picture, and we've kind of used that to propagate this thing through and understand logic and how can we think about the logic being constructed. But there are really, like, there's a bunch of additional things that you get from that in really getting an insight into, what the system is and how we can manipulate it. And so I just want to give like 1 or 2 more examples, and then we can stop for, I don't know, a few more questions and then have the break. And so one example is, like, let's say I'm looking at a 2-qubit system in a kind of 2D picture. I'm looking at these things on the plane. This is like a logical qubit. And I imagine that I have some error happening, but I have a kind of weird error where I just have an error that happens always at one location, but it happens in every time step. Now, I might look at that system and think, well, that seems kind of fine because, my logical operator, I can just always avoid that error and doesn't really seem to matter. If, on the other hand, I look in my 3D picture and I think about an error that is propagating in time, I can see that that can actually do something really bad, which is that it can connect boundaries that are sort of at the top and the bottom. So there really is no asymmetry between space and time. Maybe there is because of your physical implementation, but when I look at my actual fault tolerant channel, I can see that I really need to be understanding on an equal footing these errors that are happening in different dimensions. So this is one thing, you want to be able to really understand the actual underlying structure of the errors and the effect they have on the code. So, okay, another example is just and this I think relates back to the question someone asked earlier about looking at the geometry. which is that, you know, if you think in the picture of strictly 2D codes and doing operations on them, you're going to end up in a picture where you're always having something that looks the same in every time step. But actually, that's really not needed for these channels. And in fact, you can have an internal structure when we're building these channels that, you know, cannot be mapped back into 2 dimensions. So remember that the thing we actually really need is that this thing will like take code in and spit a code out and do some transformation in the middle. And the internal structure of that, regardless of how you create it, can, you know, have some other kind of geometry. And so this is something that can actually, you know, improve the threshold or give you other nice properties about the system by kind of thinking outside of that 2D picture. And then, yeah, one final thing, which is that, again, looking back in my 2D case at some sort of lattice surgery operation, I can think of taking 2 qubits and doing some logical operation between them. And, you know, that's fine. If I look at my 3D picture, I can again see like the thing that actually matters is the shape of this entire object. And I could, if I wanted, you know, rotate the thing 90 degrees in time, or, you know, 45 degrees or whatever. Like this thing doesn't actually matter which way it's oriented. It's always doing the same logical operation as long as it's connecting the input and output codes in the right configuration. And so, you know, even at the logical level or going upwards to the level of compiling some algorithm, you can end up with this whole bunch of extra flexibility when you're really looking at the 3D system that you're creating. Okay, so I think that is everything I wanted to say in this part. Maybe we can take a few questions now, and people can go off for the break, and then I think we're starting again in half an hour.
So I see maybe one question here. So what are the finite temperature effects on the stabilizers and membranes?
Sorry, Christoph, I missed that. Could you say that again?
So what are the finite temperatures effects on the stabilizers and membranes?
Yeah, so, okay, maybe it's useful to say this about these systems, and this kind of ties back to the fact that there's this connection with, you know, these topological quantum systems and condensed matter systems. And so this is something I haven't talked about, but when you look at kind of quantum codes, you know, or this 3D version, there are 2 ways of looking at that system. So there was a description of this system, which is, you know, assist and some logical operators. And these 2 fields get studied quite closely together. But one way is that I say that this thing is actually you know, an energetic system. So I have some Hamiltonian that is, you know, basically the sum of my stabilizers. And so I'm treating like every one of these stabilizers as some excitation in the system. And, you know, this is actually a description of a physical system with a Hamiltonian and an actual energy description of what is going on. And so when you think about that being in a finite temperature, you can think of that as being equivalent to the kind of introduction of these Pauli errors into the system, but it's in a very physical sense. So the generation of an excitation of, you know, a stabilizer and some error string is actually like an energetic property, and this thing really has some like energy associated with it. The way I've been talking about it and the way these codes are generally thought to be implemented in practice is actually, although there is, you know, you have the same kind of description of the operators, there isn't actually a physical Hamiltonian, but rather you are sort of simulating this system by making measurements on the state. So you measure these stabilizers to sort of repeatedly project your system of otherwise non-interacting qubits into something which sort of shares some of these properties. And so in that setting, you know, the temperature, it has some kind of connection to what is the rate of your errors, but the things are not actually physically interacting except by the way that you are choosing to interact with them. So I don't know if that really answered the question. I think, you know, the answer is that the finite temperature in this kind of energy model has a relationship to the emergence of like Pauli errors or measurement errors in this measurement base. And those things, you know, they kind of light up, like you see them by the stabilizers that have their parity flipped. And that setting kind of exactly the same as it does in the 2D. So, you know, in my 3D picture, I can have error strings and stabilizers that travel in 3D, kind of that behave exactly the same as the ones we saw in more detail in the 2D model.
Then there's a reference question. So can you give some reference about these fault-tolerant channels?
Yeah, so I think, you know, in a sense, it's any paper that is looking at logical gates, although they're often not described really in this way. So like of the references I have here, let's see. So this paper from Ben Brown and some others is quite a nice picture that ties together many different ways of implementing these topological features. And it has some kind of pitch in this framework. And then the other one that, I don't know, maybe I can maybe post a few of these in the Slack channel as well, since I know I'm scrolling around quite quickly. And then the other one that might be relevant for looking more like at the channel itself rather than the logic is this one, which looks at these structures that sort of go beyond just repeated measurements on a code, but to look at the structure of the channel itself. Another one that actually, I mean, that like it has from much earlier that has many of the kind of same things as this with different geometries is the kind of first paper on the fault tolerant one-way quantum computer, which I referenced at some point earlier on. And that was, you know, looking at the cluster state implementation of these fault tolerant channels and how you can like create punctures and braid them together, which is, you know, another way of implementing boundary conditions in order to manipulate logic.
And maybe last one before going to the break. So can this be applied to every type of qubit architecture?
So the short answer is yes. And in the next part, I'm going to kind of look in more detail at an example or a couple of examples of that. And okay, I guess maybe there are a few caveats that when you start like reality into this, then sometimes you find ways in which you deviate from this precise model. So, you know, if errors have certain correlations in, then maybe that's going to slightly change the structure of the thing. But actually, I think for every physical system that I'm aware of, people have designed architectures that will build this or, you know, something which is very closely related to this system to do fault tolerance. So fault tolerance based on the surface code.
Okay, so thank you very much for this first half of the tutorial and for attending. So we'll be back at 6 for the next session. See you then.
Awesome. Thanks very much.
Welcome back to the second. Okay, so hello everyone. Welcome back to the second part of the tutorial. So it's my great pleasure to introduce Naomi Nickerson from PsiQuantum, and she will continue to talk about the architectures for fault-tolerant quantum computing. So the floor is yours, Naomi, please.
So thanks very much, and welcome back, everyone. And I'm going to dive straight into the next part of this, and maybe just to recap what we saw in the first half, in case there's anyone out there who chose not to get up at 7 a.m. on a Saturday morning because they're over here on the west coast of the US like me. Really, that first part was just telling the story of starting with quantum error correcting codes. So we looked at this example of the 2D surface code, looking then at how we can actually use those to do fault tolerant operations by building them into these 3D fault tolerant channels, which are the thing we really need as this substrate for doing quantum logic. And then kind of looked at how you could actually manipulate those channels to be able to do something which is non-trivial. So this was the outline of that first part. And in the second part, the goal is really to take this, which is a theory and doesn't have any practical details underneath it, and look at the implications of how we can get there starting from something which is actually real. So what happens when we start to think about the fact that maybe we want to use superconducting qubits to try and assemble this? What are the implications? What are the operations that we can really do? And so I'm going to go back to this picture of the stack of the quantum computer, and we can kind of look at this bit that we saw so far as being these top three boxes. So we looked at the kind of general idea of this fault tolerant channel. We saw kind of decoding and the role of classical processing in that, and how you can assemble those into logical gates. And the bit that we want to kind of look at now is what happens down here. How do we actually get up to constructing that fault tolerant channel from things that are actually related to physics? And so there's a few different stages there. I mean, at the very lowest level, we want to understand how is quantum information actually encoded in some actual physical system. So I think in this picture, this is kind of representing a trapped ion where you have some energy level that's in that system, and you can identify some two-level system in it that's going to be your qubit. Then on top of that, you have to define, how do I actually interact with this system? So what are the physical primitives that I can use to manipulate quantum, manipulate those qubits to entangle them with each other? And then the next part is then this piece which links the primitives of your system with the goal, which is this fault tolerant channel. And okay, so this is an example, which is, if we're really focusing on the surface code in this kind of a system, maybe that means assembling these gates that we have into small circuits that are then going to be the building blocks of that fault tolerant channel. So this is the kind of general picture. And, actually, depending on your physical system, these pieces might look very different. And I'm going to actually talk about in more detail first a different example that might be something which is less familiar to people in general, which is starting from photons. So this is the work that I'm really focused on, which is understanding how to go from photons through this whole trajectory to a whole quantum algorithm. And again, the thing is that these things that we've already looked at, these general principles of fault tolerance, they're all the same. And the physical operations that we're using and the way we assemble them into components is going to look completely different. We have very different physics underlying it. But I'm kind of hoping this is an example which, because it is maybe different from the cases which you're more likely to have focused on before, it emphasizes this idea that the fault tolerant channel is, really it's a description of what is the correlation structure of the system that you're building. And then there are many different ways of getting there. And by kind of digging in to look at the physical operations that we actually have access to, we can figure out a scheme from sort of going from those things up to this fault tolerant channel. So that's the goal. And before I get into that specific example, I guess I just want to start by talking about what is the process that we're actually going through here. And so this is pretty general kind of set of steps that you might go through if you want to go about constructing a quantum architecture for your. So regardless, this was going to someone's question from earlier, can you use any kind of qubit system to build one of these fault tolerant channels? The answer is, well, if you have a universal gate set of operations, then yes, you can. And maybe a different question is, well, what is a good way to go from those physical primitives to the thing we're after? And so the steps go something like this. We start out with our target. Like, this is what we want to assemble this. first thing I want to do is kind of look really closely at our system and understand what primitives we have. So what are the basic building blocks? Like, what are the building blocks of entanglement? What are the building blocks of the operations that we can actually do? And ideally, you kind of, also look at, well, what is easy and what is hard? What is a clean operation and what is a noisy operation? And use that to kind of motivate your scheme. Then once we've figured out what those primitives are, we then want to understand how we can assemble those to build up to large-scale entanglement. So whichever system that we're starting with, it's always going to be the case that our primitives are these sort of small operations. So maybe we're going to have the ability to do 2-qubit gates or make projective measurements on some small number of qubits. But they're always going to be small. And what we need is this very large scale entangled correlated system. And so this stage is really about figuring out how we're going to assemble those building blocks to get this large entangled structure. Okay, so after that, like at this point, we're still sort of talking in a semi-abstract way. We've got physical operations, but we're just talking about entanglement. And so the third piece is to look at how we can take that and actually fit it into actual space and time. So maybe we have some kind of sense of the state or a circuit of things that we want to run. But practically speaking, you're actually going to have some piece of hardware, and maybe the components like have to fit into 2D space. Maybe they have some restrictions on how they can connect together. And so this third piece is about how do you actually embed that, and does that have any sort of implications for the way that system behaves? And then the final piece is, once we have that, this kind of finishes our assembling our quantum architecture. And the final piece is then to, like, given that we've constructed that, to analyze the errors and understand how the thing actually behaves. So we were previously looking at this kind of simple toy error model, which is really helpful to understand sort of the basics of how things behave, like how do these error chains appear? What does a syndrome look like? But they really just don't bear any relation to reality, where the errors are going to come from a whole bunch of different places. And so the final step is to do that. And the output of this procedure, once I've assembled this thing and analyzed the errors, is that we get out some actual fault tolerant channel. So we had some target that we were going after, but when we piece all those things together, we'll get out the thing that we're really building, which, and I'll kind of look through an example in much more detail. So maybe it looks kind of similar to what we were after, but maybe it has kind of a whole bunch of extra edges added that represent different errors that might happen. And maybe there's some asymmetry in it. So maybe some of the errors are different. And maybe there are some, correlated structures of error that are going to behave differently than, what we were targeting. And so this procedure, by going through all these steps and ending up at an understanding of what we're actually able to build based on what we have, this is then the starting point for being able to kind of go back to the beginning and say, well, given that I can see how this thing actually comes together, well, what can I do that's better to engineer my process to do this as well as possible with the operations that I actually have access to? Okay, so this is the principle, and this is completely general. This is something that you can take whatever system you want and apply those kind of principles to get to some architectural design. But the one that I want to focus on now is looking at how we can do this starting with photons. And I think this is a very different way of looking at where the fault tolerance comes from. And that maybe helps to kind of see that the way we construct these channels can come about in ways that are physically very different, even though you're going to end up at somewhere where ultimately we're just getting some kind of particular structure of correlated measurement outcomes. So I guess just to say a few things about photons, there's, often when we think about a qubit and these examples that I kind of gave in the previous half, you think about, a qubit as like an object which kind of statically sits there and it has some state and it persists, and maybe I can interact with it, over multiple time steps. The thing with photons, of course, is that they're not static. They're constantly traveling at the speed of light. So you're really not in this picture of qubits that kind of sit there and you can interact with. And the other thing that kind of changes how we think about them is that a measurement of a photon destroys the photon. So if we want to go and make a measurement afterwards, the qubit is just gone. So we have destructive measurements. So those are two things that kind of move you out of this maybe more standard picture of kind of being able to do repeated gate operations. There's a few other things just to say about photons, just in general, as an approach to building up these channels, which is that the error model looks pretty different than what you might have if you're starting with matter qubits, and specifically these Pauli errors. So these bit flip type errors are very small, and this happens because photons don't interact with their environments. They don't interact with each other, and they don't interact with, they don't feel heat. And you can see this because we can still see coherence in photons that are coming from the other side of the universe that were created billions of years ago. It's still possible to kind of see the coherence in those photons. So like very different than something which is interacting with its environment. But on the other hand, photons, the real thing that you have to worry about with photons is that they are prone to getting lost. So a photon can maybe get absorbed into a waveguide, in which case it's just kind of gone. So that's a different kind of error. It's this erasure error that I mentioned briefly, where you know the location of the error. So I guess this is just to give a sense that depending on the physical system, the way your errors behave and the types of errors that are big and that are small are going to look very different. Now, photons are not qubits. A photon is just a boson. It's some excited bosonic mode. But we can make photons behave like qubits in quite a simple way. And I'm going to talk about qubit encodings of photons that are based on single photons. There are also other approaches that encode these states in a different way, and like for example, GKP codes, which you can use to create these kind of continuous variable types of photonic qubits. But I'm going to be focusing on these ones that use single photons. And there's a bunch of reasons for that, which maybe I'll say a few things about a bit later. So okay, so the photon is not a qubit, but we can make it act like a qubit by taking our one photon. So this is now going to be a photon, and putting it into one of two photonic modes. So these could be like literally just two waveguides, or any two places that the photon can go, and we're going to call one of them 0 and one of them 1. And so if the photon is in the top rail, this is a state 0, and if it's in the other one, then it's a state 1. So really, this is just a way of creating kind of an effective two-level system, except now there's no energy involved. It's really just about location. And then you can do single qubit operations by adding some kind of interferometer onto this qubit to manipulate the state. So this is our starting point. And I guess I'm not going to go through in a ton of detail how you build this thing up, because linear optics is a whole different topic. This is just to give a sense of what the starting point is. But I want to jump in and look at these primitives, because this is the place we really want to start, which is to understand from the perspective of fault tolerance, what are the natural operations that we have access to. And it turns out that the thing that is really natural with these photonic states are two things. So the first thing is the ability to generate some entangled states. And so we can kind of have some linear optical system. So this is some system that, we have a bunch of single photons that go into it, and it does some kind of, procedure in here. And out comes some kind of entangled state of some small number of photons. Now, this is just a convenient way of thinking about things because of the way entanglement generation works with optics. And it really just leads us to think about these things as the sort of one of these primitive operations to build up our computation from. So here I'm going to use the graph state notation because it's a convenient way of describing these small entangled states. And so the graph state notation is just a convenient way when we have like some particular structure of entanglement, we can represent it as a graph where these vertices are the qubits and these edges are sort of entangling, let's call them entangling bonds. And the construction is that it's actually a very simple rule. It's just I take a plus state for every one of these vertices, and then I apply a control Z gate between those two qubits, and then that leads me to have this state. Now, in the photonic case, you won't be producing it with this set of operations. You produce it in some other way, but it's equivalent. Okay, but there's another way of describing these states, which is going to be much more helpful from the perspective of understanding its fault-tolerant properties, which is to use stabilizers to describe the state. And so if we take another version of this state, rather than describe it, by the state and the operations we use to prepare it, we can instead say that we can use these stabilizer operators. And remember, these are the things that sort of act trivially on this state as a description for the state itself. So as with these error correcting codes where it was like very convenient to use these operators to describe the system rather than having some crazy state vector, same thing is true here. And the stabilizers that describe one of these graph states also have a very simple construction, which is that we take an X, a Pauli X operator that's centered on every qubit, and then a Z operator that is on all the qubits that are adjacent to that site. So this is one stabilizer, and I'm drawing this line to sort of indicate that this is the tensor product of those two things. There's another one, which is X on the central qubit, so X, Z, Z. And then there's another one, which is on this final qubit. And if we have some different graph state notation, we can use the same rule to identify what these stabilizers are. Okay, so this is our first primitive. We have some kind of system which is going to produce some small entangled states. But of course, if all we have is small entangled states, this is not enough because what we're after is entanglement. And so the second primitive is to look at our entangling operation. And here is where, things start to look a bit different. So if I have, say I have superconducting qubits, or any qubit where we think about a gate model, you think about a picture where I can take two qubits, Psi1 and Psi2, and I can, do some entangling gate, which produces some entangled state at the output. But with our photons, our measurements are destructive. So we kind of saw this at the beginning, that if we make, if we make a measurement on it, it's destructive. And it's also not possible to build this kind of entangling operation. So with photons, and I'm specifically talking about this kind of with the linear optical operations, and in this setting of the single photons, there are no entangling gates of this kind. So photons do not interact with each other. We can't, they don't see, they don't see their environment, they don't feel heat, they don't interact with each other. And so we can't directly get the photons to interfere. But there is something that we can do with photons. And let's say we have, two photons as part of one of these states. The thing that we can do is make a measurement on the qubits. So I can take these two photons, and I can measure them with a joint measurement that is going to give me 2 measurement outcomes. And I'm going to look at an example where it gives me 2 outcomes, x1, x2, z1, z2 on these 2 qubits, where the measurement is an entangling measurement. Okay, so there's a big difference between these 2 operations, right? In the one case, I'm putting in 2 qubits and I'm doing something entangling, and at the output, I have 2 entangled qubits. In this case, I'm doing a destructive measurement, so the qubits are gone afterwards. But what I get out is 2 measurement outcomes that correspond to an entangled state. So, to give a few different ways of describing what is happening here, this is a joint measurement on 2 qubits where it does a projection onto a Bell state. So it's doing a projection onto an entangling state. Or another way of looking at it is that I get these 2 measurement outcomes, which correspond to like these 2 stabilizer operators that themselves correspond to a Bell state. And so the reason that I think it's helpful to look at this example in relation to this fault tolerant channel is if we think back to what it is we're actually trying to do, which is, construct this big block of classical measurement information. This is ultimately what we're after. We put a code in and we get a code out, but in the middle, we're doing a bunch of operations, we're doing a bunch of measurements, and that's what we build the channel up from. And so, when we think in this setting, we can see that actually this is just fine. This entangling measurement, it might destroy the qubits, but it gives us entangled measurement outcomes. And so that is a primitive that then we can use directly to try and build up these channels. And this is by kind of really thinking about what it is that we're trying to get in this system. Okay, so let's go on to looking at how we can take these primitives and use them to build up to large scale entanglement. And I'm going to be using an example that is in this paper, which was kind of recently on the archive. And I'll also comment that there's a talk happening later in the week from Mihir Pant that's also going to talk on this topic, and he'll talk in a kind of much broader sense. I really am just going to take this one example and look into how we can use it to get this kind of the right correlations in measurement that we're after to build up to fault tolerance. And so the basic idea of this is that we have our one primitive, which is all these small entangled states. So we can have a bunch of those. And then we have our other primitive, which are these projecting entangling measurements. And so the idea is quite simple, which is that we can get some array of these states and we can do projective measurements on them. Every measurement we do is going to give us some, entangled measurement outcomes in the sense that it's projecting onto an entangled state. And if we arrange these things in the right way, and we have the right states and the right measurements, then those things can form this fault tolerant channel. So, and what that means really is just that we have the right structure of correlations that is going to propagate logical information and going to give us parity checks. Okay, so let me go into this example. So what we're going to start with here is rings of 6 qubits. So this is a graph state in the same way that we looked at before. Now it has 6 qubits and they're connected together in a ring. And this thing has stabilizers. Let me do these in blue that look like this. So it's an X on each qubit and then a Z on the neighboring qubits. And then there's one of those for every different site. And we're going to take two of those states and put them on a unit cell that's then going to be something that we can tile out to create some big array of these states. Now, this is just kind of setting up an arrangement of them where we're going to be able to later see the link back to the structure of the fault-tolerant channel that we're building. And I think like the thing at this point is that you do not really see how this thing is linking back to a surface code. Like there's some, it's sitting on a square grid. But to see how those things link together, we need to add these measurements that are then going to extract the information that we need to get correlations out. Okay.
Naomi, can I relay one question before moving on? Yeah. So in the previous example with 6 qubits or the 6 vertices, there was a question that is asking, like, if we measure the 2 vertices, then only 4 are left. And the question is how those remaining 4 are entangled. So can you elaborate a little more on that, please?
So we're talking about this example. So, okay. Maybe I'll do a slightly different example. Let's say we take 2 of these states, and we do some joint measurement on these. So I'm going to measure the operator. Actually, let me change it slightly. So we're going to measure the operator xz and zx. So it's also just a slightly different projection. After we've made that measurement, one interpretation is that I am left with an entangled bond that has been created. So I've got some new state where the 2 qubits that I measured, they've disappeared because I've measured them away. But since I did an entangling projection, I'm left with an entangled state. So you can always have an interpretation like this where I look at the entanglement that is left behind. So it is one way of like kind of interpreting what it means that it's an entangling measurement. On the other hand, this representation is actually going to be much more convenient to think about when we're trying to think about what is the structure of the information that we're getting out overall. So if I take some big network of qubits and I do a bunch of fusions and I try and figure out what is all the entanglement I have left behind, it's going to be some like really complicated state that I have no chance of drawing. But if we just stick to looking at this measurement information and understanding what its structure is, like looking for what the correlations are, and I'll be very explicit about what I mean by looking at the correlations in a minute, we'll be able to see that those measurements themselves have a structure that corresponds to the ones that we were trying to get out in that syndrome graph. So, I mean, which basically just means that I can take some combination of them and they're going to give me parity checks. Okay, but thanks for the question. I hope that is helpful. And I think just what I'm going to do is I'll go through that. I'll set up what this thing looks like and how we can kind of construct this thing, and then I'll pause and see if there are a bunch of questions to answer them before I move on. Okay, so let's look at this. We're going to do a whole bunch of these measurements that are of the type that I described. So they're doing a sort of a measurement of 2 operators, XX and ZZ, on 2 qubits. And I'm going to do those on these states that I've laid out. Now, here you can see there are a whole bunch more qubits, and what is happening is that there are, here is a state that was part of this unit cell. This one, but then there are states that are sort of belonged to a neighboring cell when we tiled this thing out. So, here are three qubits that are from the state that got stuck on, from the next cell over. And what we're doing here is trying to understand what is the structure of the stabilizers when we take the fact that we've got some states which have stabilizers and some measurements. so we've got these states and measurements that both have stabilizers. They're going to get combined. And in the end, what we're going to be left with is a whole bunch of measurement information that has correlations in it. And we want to understand the structure of those correlations. And so the thing that we want to do to understand it is look for the parity checks. And so I've set up one very specific example here, but I'll just say that, you know, this idea is very general. If you have different physical operations, you know, if you have gates or circuits or different kinds of measurements, what you're always doing when we set this thing up is then trying to figure out, well, where are the parity checks coming from? What are all of the physical operations that are actually feeding in to those things that I'm getting out? And that's what's going to tell you really what is the structure of the system. Okay, so let's look at this example. And I'm going to start by zooming in on one face, this first one. So what we can see here is that we've got one stabilizer here that's corresponding to this state. So XZZ centered on this qubit. And then we've got another one, which is centered on this resource state in the bottom left, which is also, you know, X on this center qubit and ZZ on the ones on the outside. And these are, you know, two separate things at this point, but then we've also got this, this entangling measurement that we're doing. And one of the measurement outcomes from that is this XX. So this joint X operator on these two different qubits. And so if we combine all of those stabilizers together, you know, these Z's on the outside, they just stay the same. But on these qubits in the middle, we have, you know, an X being applied twice. So we have this X, and then we have this one. And of course, X squared gives us an identity. So these things sort of, you know, cancel out. And the same thing with these two. And so, you know, when we take the product of those things, we're left with just Z on the outsides, of this face. And so I can do like the same thing over on this face on the left. So I have one stabilizer, which is XZZ centered on this qubit. I have another one, XZZ centered on this qubit. And then I have another one of these entangling measurements, which gives me an XX outcome. And again, like the X's are going to cancel out. The X's are going to cancel out here. And I'm left with Z's on the edges. And so I can imagine doing this procedure for all of the different faces. And what I'm left with at that point is just a bunch of Z operators on some of the different faces. And now, I guess there's one other thing that is kind of missing here, because I'm kind of left with these bunch of Z's, which is to point out that the other thing that our fusion does, so if I focus on this fusion right here, sorry, fusion or entangling measurement, the other outcome that I'm getting from these measurements is the ZZ outcome. And so this one now is going to kind of overlap with this Z and cancel it out. And this one's going to overlap with this and cancel that out. And then, you know, I'm going to end up with the same thing here where I have some other fusion here. And so I can kind of go around the whole cell and, you know, combine all of these different measurements and think of it as sort of gluing together the stabilizers that are on all of the different faces. And once I've combined all of those things, they're going to add up to identity. And so this is telling me that I have a parity check. By finding this combination of the stabilizers of these states and the measurements that's summing to identity, that's what's giving me a parity check. Because another interpretation of that is if I, you know, combine the measurements of, you know, this measurement outcome and this measurement outcome and, you know, this whole set. So I take the ones on the face and the ones on the boundary and I combine all of them together. Then the combination of those measurements, so, you know, like if I take M1 and M2 and all the ones through to M, the last one, then the product of those measurements, which remember are actually classical measurement bits, should be 1, because if I take the sum of them, I get an identity. And so this is the definition of the parity check. So I've found my parity check, and it's now made up of not some, you know, toy model, and not some kind of assumed large-scale entanglement. It's made out of physical operations that I'm doing, you know, out of the primitives that actually belong to my system. Okay, so maybe I want to pause there and see if there are any questions on that, because this example is maybe a bit complicated, and then the stuff that comes after is more sort of building on top of this.
Yep. So there were several questions, but the one that's relevant to this specific discussion is how does this measurement and parity check relate to the surface code that was discussed in the previous section?
Yeah, so I think that's going to become clear as okay, so I guess we can just look at this example and see this, which is, I can think of there being a parity check associated with this cell. You know, I've taken this kind of combination of measurements that are wrapped around it. And you know, so, you know, I've got a whole kind of bunch of things that are like, measurements that combine to give a parity check. Now, I think it's fair to say that you can't see at this point like how that emerges into the large scale thing, but I'm gonna work through that example next. So that'll probably just answer much better than I could now. Are there any other questions on that stuff?
Yeah, let me check. So there were some other questions like, is it possible to just do the entangling operations rather than entangling measurements in linear optics? That was one question.
Yeah, so with linear optical operations, you cannot generate entanglement. You cannot do a sort of entangling gate between two qubits. And that's because photons don't interact. They interfere, but they don't interact in the way that you can kind of like do a unitary entangling operation. And I think, you know, at first sight, that seems like a kind of problematic thing. Like and I think the point of this example is to get across that given that all of error correction is about measurement, it's all about measurement. You're repeatedly measuring, you're making like measurements that are kind of generating a certain set of entanglement on your qubits. The entangling measurement is a primitive that you can use actually just as well to get out the type of entanglement, like the type of correlations in measurements that you need. So yeah, the answer is like, no, you can't do entangling gates on qubits, but you know, maybe just to look at this example, like a kind of very similar but equivalent thing might be to take these things, do an entangling gate between them, and then measure these two qubits out in the X basis. And this would actually do exactly the same operation as this entangling measurement. It's actually, I think, then maybe a little bit harder to see how the stabilizers add up. But those are kind of two equivalent sets of operations.
And I want to relay one more question about this entangling measurement. So there was a question about like how we actually physically do this entangling measurement in a photonic setting.
Yeah, let me just do that. And it's actually, one of the reasons that it's like to use this as the primitive is that entangling measurement is something which is very easy to do with linear optics. And so, okay, I've got in the system, I've got two qubits. So psi1 and psi2, and each of those qubits is two waveguides. So these like two waveguides where there's maybe, you know, one photon in some state. To physically do that projective measurement, you need to take your qubits, put them through a beam splitter, and actually need to do this on both of them. This is a terrible picture. And then I do single photon detection. So, and that's the whole circuit. So beam splitters are extremely easy to do. And this is, you know, a photon detection operation that counts the number of photons in that mode. And this does that projection. Now, another thing maybe I should just mention about this, because it's probably something people know about linear optical operations, is that with these physical linear optical operations, this thing actually succeeds in a probabilistic way. So, you know, in some setting, it might correctly do the projection 75% of the time, and the other 25% of the time it does not generate entanglement, it does something else. And the setting I'm thinking about here is that, well, okay, this imperfection is one of many types of imperfections in a system. And this is something that fault tolerance can deal with. So if you have, just to like, when you're really looking at the physical linear optical operations, there's this what gets called linear optical failure. But this is something that we can just think of in the context of all of the other things that are going wrong. So there's going to be loss and errors and Pauli errors and all sorts of things going wrong. And this can be handled by the fact that we're constructing this fault tolerant channel. Okay, so maybe I'll go on because I think that'll, I think the question of how does this relate to the surface code is a very good one. And I think it's not clear at this point, but hopefully it will soon become clear. And so, okay, what we were looking at here was where do the parity checks come from? And really the next stage in trying to understand the structure of the system we're building is to look at the effect of errors. Because, if we think about the syndrome graph representation of our, of our fault tolerant channel, this big kind of cubic thing, what this actually is are like vertices are the parity checks. And then the edges are the edges are errors. So anytime that there's an error, we have some edge in this graph that will lead to parity checks to have their value flipped and show up as having odd values. And every one of those things kind of is represented by some edge in this graph. And so this is now kind of what we're trying to do, which is like we found the parity checks. So we sort of found a vertex. And now we want to understand like what's the effect of the errors, because that's going to tell me how the parity checks get connected to one another. And what we're hoping is that, we're going to end up with something that looks kind of like this. We end up with a graph. So we have errors that flip parity checks in some kind of structure that is going to lead to this kind of a graph. Okay, so let's look at an example of that. And I think the first thing I want to think about is, well, what if something goes wrong with one of your measurements? So I'm making a measurement, XX, ZZ, and what the measurement is giving me measurement outcomes. So, I get a classical bit that is the result of that measurement. And something that can go wrong is that when you do the measurement, you actually end up getting the wrong outcome because of an error. So you have a bit flip that turns up. And that could happen, because something went wrong in your circuit where you were doing the measurement, or maybe one of the detectors told you the wrong thing. There are lots of kind of physical ways. And this means that you're reading out the wrong value. So if everything had been perfect, you would have got one answer. In the end, you got something else. Now, okay, we can look at this example then and see what happens. So what we know is that if we take these XX outcomes on from every face, and then take these ZZ outcomes at the edges, and combine all of those things together, then they should give us a parity check. So there is some value that's associated with this cell that comes from combining a bunch of these like physical measurement outcomes. If one of these measurements goes wrong, so let's say that this one actually gets flipped, and so it should have given me the outcome 0, but actually it gave the outcome 1. Then because this value in this parity value is constructed by taking by adding up all of these measurements around the cell, the effect of that is going to be that the value of the cell itself, so this parity check, shows up as being, having the wrong value. It shows up as an odd parity. So the effect of some error in the measurement is that this parity check you know, gets flipped, and we can see that something has gone wrong. But the other thing that here is that, you know, if we kind of look a little bit closer at this particular measurement, is that there is another cell that sits on top of this. Like, this thing is tiled out in all directions into this cubic lattice. And so if this thing flips, there's actually a whole nother parity check that's like belonging to, you know, the thing on the top. That's a combination of these different measurement outcomes and, you know, measurements on the edges. And this particular measurement is also a part of this check. And so if there's an error in this site, then not only are we going to end up with this odd parity on this parity check at the bottom, but we're going to end up with an odd parity on this one at the top. And so those are the only two things that measurement is going to affect. You can kind of see there's no other cells that it's involved in. And so, you know, we can go back to our syndrome graph picture and say that, okay, well, there's some edge that corresponds to that, you know, that outcome XX. And if that thing has an error, then it's going to affect a syndrome which is kind of above it and a syndrome which is below it. And we can do a similar analysis for, you know, the different sites. So, you know, what if there was some error at this location? Well, you know, the effect of that is also that it would, you know, flip the value of this check. But then there's one sort of like to the front. There's a cube to the front, which also includes this measurement, which is also going to be flipped. So, you know, we can add an edge for that qubit, which is representing that, you know, our central parity check gets flipped and the one at the front gets flipped. And, you know, then this one on the right-hand side, that's going to kind of flip our center cell and one to the right. So we add some edge like that to our syndrome graph. And then, you know, with this one at the back face, well, that's kind of connecting to our center cell, but also to one like over in this direction. And so in our syndrome graph picture, that adds an edge. And then there's a, you know, another vertex for this check. And you kind of continue this picture thinking about, you know, all of the different faces. And now we see that this cubic structure is emerging. And obviously, like, this thing is kind of going to continue because, you know, the same thing is going to happen at the next cell and so on. So by looking at these errors in those measurements, we can see that, you know, we're ending up with this cubic structure, which is the fault tolerant channel we were trying to build. So, okay, so now we can kind of see the connection to this fault tolerant channel. Like, it is much harder to see the connection to the surface code itself. You can kind of think of the surface code as something which is propagating through this system. But right, remember that the thing we're really after is this channel, this object, which is going to allow us to, you know, stick a code in and get something out again and manipulate the logical information on the way. And so now we have that. But okay, this is a good starting point, but there are some things that, you know, I haven't looked at yet. And the other thing that we should mention is, well, what happens if one of our ZZ measurements goes wrong? So, you know, this is the other thing that could happen, which is, you know, our ZZ outcome should have given us a 0 and it actually gives us a 1. So we get some measurement error there. And let's just take a look at what happens with that. So, you know, remember that we're looking at kind of the ZZ outcomes on these things that are at the edges, that's sort of stitching together the different pieces of this cell. And maybe I want to look at this one in particular. So here we're just going to see something different is happening. So this is a part of this cell at the top. We combine all of these different measurements to get our parity check. And so if there's an error in this measurement, it's going to show up by giving us a parity in this cell. But the other thing that's going to happen, like, it's no longer the case that this connects to one of its neighbors. Instead, this, because it's on an edge, it connects to a cell which is, you know, down one to the right. And so when this parity flips, it's going to show up in also in this cell at the bottom. And so if we think back to our kind of syndrome graph picture, you know, we had our cubic structure, and this cell on the top right is, you know, like this one, and this other one is this one. And so the effect of this error flips two parity checks that are now connected diagonal. And so this is the first place where we're kind of seeing that we have a syndrome graph structure, and yeah, it looked kind of like what we were after. But actually in reality, and this is because the scheme is actually accounting for the fact that we're constructing the information, we're building up information from smaller physical entangling operations, we end up kind of with a bit of a different structure than what we were really after. And so you can kind of, you know, continue building up this thing, and you end up with, you know, a whole bunch of diagonal edges in different places that correspond to these Z errors in these Z measurement outcomes. Okay, so the result of all of this, you know, we can kind of continue through this example and get to build up this whole syndrome graph, and we end up somewhere like here. And so now we've sort of arrived back at this picture that we're familiar with. So we have a syndrome graph. We have, you know, parity indices, which are parity checks. We have edges, which are representing errors. You know, in this case, they're representing errors in measurements, but it's a physical operation. And this thing is represents a fault tolerant channel. Okay, so maybe I just want to mention a little more about errors, because I've talked about, well, what happens if there's some error in the measurement? You know, in practice, there are tons of different ways that errors can happen. So another kind of obvious way that we should worry about in this example is, well, what if there's an error on the state itself? So maybe, you know, you're preparing the thing and something goes wrong, or you have some imperfections in your components when you're preparing this entangled state. And so another thing that could happen here is that, you know, my input states are actually not perfect, but maybe some qubit has a Pauli Z flip on it. So this is kind of going back to this idea of a Pauli channel being errors that get randomly applied to some qubits as a model for some of the things that can go wrong. So what's going to happen if one of these states has an error? Well, okay, let's say it's happening on this state in the bottom left. So before we get to do our measurements, that state has an error applied. Well, the effect of that is going to be that this Z anti-commutes with this X measurement that we wanted to make. So even if the measurement itself is perfect, its value is going to be flipped from what we expected because it's anti-operator. And so actually kind of what you can see from that is that this Pauli error, which is applied, you know, on a qubit of the resource state, actually has exactly the same effect as there being an error in this measurement itself, which is the that we already looked at. And so if we go graph and kind of look at how that corresponds to edges. So we had, you know, some edge here that was, you know, the fusion, the error. But now we've just seen that there's like a completely different error that causes the same set of parity checks. And so we could go and add another edge to that graph where, you know, this edge is now the like Z flip on the state. And so actually just, you know, going back to here, you can see there's another thing that could happen, which is, well, what if there was a Z flip on that qubit of the other resource state that's going into this fusion? Well, and there wasn't one here. Well, that would have also exactly the same. So it appears in the same way. And so, you know, maybe there should be another edge on here that corresponds to that other error. And so I guess that like the point of this is that when we look at a toy model, we choose a model which kind of is representing all the different configurations that can happen. So maybe it's representing every edge. But when we're looking at a physical system, which has many different physical sources of error, which maybe kind of occur independently or, you know, appear in different ways, then that it can be the case that there are many sources that lead to the same configuration of syndromes. And so when we're, you know, looking at these edges, maybe it's the case that, you know, some of them have different error probabilities because all of these different physical sources are going to contribute to kind of a different configuration on this graph. And this goes back to this question of, well, what really is the geometry of the state? Because this isn't something that we can just freely choose. To some degree, it's going to be dictated by the operations that we actually have available and the way it turns out when we assemble them and actually analyze the things that can go wrong during those procedures. Okay.
So Naomi, I think you've already answered some of the questions that are being posted on Slack, but let me just relay to bring that to your attention. So there was a question which is asking, like, how do we recognize that this specific 3D structure is a fault tolerant channel? And another related question to this is why is there just one type of diagonal, not the other type pointing the other way?
Yeah, okay. So the first question was, how do we recognize that this is a fault tolerant channel? And this goes back to this sort of analysis of errors, and I've been through a few of them. But the way that you can convince yourself it's fault tolerant is by, you know, really going through every type of possible physical error that can happen. So, you know, and this means I define some error model, and maybe my error model is that, you know, every measurement in every fusion can potentially give me the wrong outcome. And every qubit on every resource state can possibly get a Z flip or an X flip. And then I can go through every one of those different error instances and look at how it turns up and turn this into a syndrome graph. And if my syndrome graph is really representing every possible error that can happen, and it's, you know, and I can see that it's still local and it still has this sort of structure and there are no errors that sort of got missed and didn't get captured, then I can say it's fault tolerant. And I guess the question that comes after that is, well, how well does it tolerate the errors? And for that, you really need to get into doing numerical simulations to kind of study the performance of those errors and how well you can tolerate them when you include decoding. And so it's something that you can also numerically check. And sorry, I've forgotten what the other question was. Oh, diagonal edges. Yeah. Yeah, and so this is an interesting one, and actually I want to come back to this again a bit later. This is really coming from the actual structure, like the way that you're building the entanglement. And kind of what is happening here is, okay, it's easier a little bit to see by looking kind of at the flip problem, is that, you know, these two things are already entangled as part of the resource state. And these two things are already entangled in the resource state, but like here, they're not entangled. So you know, this sort of thing, you're generating the entanglement through your measurement, and the same thing is happening here. And so these diagonal lines, as like, I can think of these as, you know, here is a line where I have to make a measurement to kind of connect two things together. And so it's kind of a feature states that you started with and the fusion, these measurements that you're making that creates that in a particular way. And I think things is that, okay, I'm looking at a particular setting here with states and measurements. If you build up a circuit starting with, you know, qubits and gates, and you measure parity checks, you also end up with a very similar thing with these diagonal edges. And maybe I'll say a little bit more about that later on. Okay, cool. Thanks very much for the questions then. I think I'll I'll go on. So yeah, this is just a quick aside to mention that one thing that I've really skimmed over the whole way through is that when we look at building up these channels, there are really these two parts to it. So there's a primal part, which is, I can think of as the part which looks after the X membrane, and there's a dual part which looks after the Z membrane or supports the Z membrane. And I've really only been talking about one part and one syndrome graph, but there are syndrome graphs. And to kind of go back to this example, the part of the physical measurements that I've really skimmed over is, well, what happens if I take my X outcome here and my Z outcomes on the center faces? And the answer for that is that, actually these things form an identical problem with its own syndrome graph, where the syndromes are sort of centered at the vertices. So there's this kind of duality relationship between the one that I've been describing and this other set. And so, yeah, when you do this process of, actually going through every possible thing that can go wrong and all of my different measurements, I would of course have to account for the errors in these, and they're showing up in another but identical copy of this syndrome graph. So this isn't like, for understanding most of the things that go into this is not kind of critical, because the two problems end up looking identical, at least in this case. But it is kind of critical to know that there always have to be these two components to make it a quantum code rather than a classical code, like one for the X part and one for the Z part of this logical qubit. Okay, so great. Now we've kind of looked at this whole example of how we can take entangled states, we can do measurements. We've started with physical primitives and we've stitched them together to create this fault tolerant channel. And now we want to go on to this third step of understanding, well, where does physical reality come into it? We've been just talking kind of with abstract states. They could be connected kind of however we wanted. And in practice, we're going to have to build this thing from a physical system. And I guess the thing to kind of highlight about everything we've talked about so far, like throughout this whole thing, looking at fault tolerant channels with any system, is that the thing we're after is this 3D structure. And in this case, we've got some kind of 3D array of states that we're going to measure. But there's no prescription to which order you have to do those operations in. We need to do, but there's no, there was no feed forward happening. There was no like measure this and then change the way you interact with something later on. And so with freedom to really go about doing those set of operations in whatever order is most convenient to turn it into something physical. Okay, and this is something that we can really use to make our lives much easier when it comes to building an architecture. So way would be that we create all of those states at the same time. So you create this kind of whole 3D block, you somehow like wire the things up so that everything can like undergo the right measurements with the right other things. And we could do that all in one step, but this might kind of less than we might want. But another way that's kind of like a natural way of simplifying that is that we instead create a layer of these things in time step one, and then we kind of do the operations in that. And then in the next time step, we can use the same kind of physical system to create a second layer and then connect the two together. By which point, like, we'll be done with this first one. So, these ones have kind of been destroyed. They've been their photons, so they've been measured out. And then we can make a third layer, do interactions between these ones. Then we'll be finished with layer 2, that will be gone. And, this process can kind of proceed. And this idea of reusing, like the best way of reusing your physical resources is, this is really critical to the idea of a quantum architecture. Like, we're starting with some, system that we're trying to build, but where are the flexibilities that we're doing? These fault tolerant channel in itself is pretty flexible, what order we can do the operations. And so we can make those choices to be something which is going to be physically convenient for the system that we're building. And so, I'm going to look at an example, and this is the example that corresponds to these layered things. Into is some actual layout of how we might arrange things in a device so that we can do those operations. This is corresponding to that picture above, and what you can kind of think of this of is we have a number of boxes which are resources. So we have some physical device which is going to create copies of these entangled states. And so we can think of that as in each time step, this thing is creating one of these rings. We'll have one here and all the other places. And then these qubits are gonna, because they're photons, they're gonna fly immediately as soon as they're created. They're gonna fly at the speed of light along whatever waveguide is next to them. And here, these two things are gonna enter this box, which is labeled F for a fusion, which is going to do this projective measurement. So we'll have, there's some like ring here and ring here. And this qubit at the south is sort of going to connect here, and these two things will get connected. This one is going to go here, these ones will get connected, and so on. So we're creating a layer of these states, and they're getting connected together with physical operations. Okay, and then I guess the one thing that is missing is, well, what is happening to these qubits here? Well, this qubit is going into some operation, which is right here, but this other qubit is going into a short delay line. So that's all that's being added here is like some short delay that makes this qubit wait for one clock cycle. So that what ends up happening is that, in the next cycle, I'm going to make a whole nother set of these layers. So, I have a new resource state here. Maybe I should use a different color. Let's go for red. So I have a whole nother state get created in the next time step, and, one over here and one over here, one over here. And at that point, this qubit is going to arrive at this fusion at the same time as the qubit from the last clock cycle. And so I can end up doing a fusion that connects two things created at different points in time. Okay. And so, you can see this thing can kind of go on. You create different layers, and I'm stitching them together. And so this is implementing this picture here where I've introduced time into this structure as a way of, simplifying this layout so that it's two-dimensional. And, sorry, this thing is very messy now, but it's two-dimensional. Things are connected only to their nearest neighbors. Like, I'm creating a 3D system out of something which is two-dimensional. And maybe I'll just make like a few brief comments about, firstly, just about logic, which is, okay, well, this is something which is creating, some bulk. And at the moment, we just talked about all the operations being completely identical. And what we talked about in the previous half was, well, at some places, we want to do something which is non-trivial. Like maybe we want to introduce like a defect that modifies the membranes, or we want to introduce boundaries. And so for that, physically, that just turns into some sequence of instructions about how to interact with your qubits on different time steps. So, in this example, I might have a layer where I'm doing, normal things. I'm just doing the measurements I would always do to get these parity checks. And then in some special layer, I flip a switch. I do a slightly different measurement in such a way that, I'm changing the boundary conditions in some location. And so physically, that's how logic turns into these operations, which is just a small modification to the operations at a certain location. And so, yeah, there are a few talks happening, a couple during this week that are kind of relevant. There's one talk that's really digging into log operations, and particularly the non-Clifford operations that you need to do. So that's Michael Beveland's talk. So that will like talk in much greater detail about those logic and thinking about it, kind of the real implications of those things. And there's another talk from Kiana Wan that is looking at other ways of reusing physical resources, because this is really just one way. And in fact, you know, there are many different approaches of how you could reuse physical resources. And so this one might be interesting. It's a kind of very different setting, but kind of using the same idea of how can you like repeatedly use a resource to generate these fault tolerances in a different way. Okay. So then we can come back to this question of analyzing errors. And we've actually done that already. We found the syndrome graph. But when you take the system and embed it into, you know, physical reality with time and space and maybe like restrictions on how you can connect things together, this can add, you know, another layer of complexity to the way that those errors behave. And so we need to go back and kind of revisit this structure and see if when we, you know, stuck things into you know, this actual physical picture, did we change anything about the way the errors behave? And, you know, in this case, something is going to change. And what is going to change is that not all my qubits are going to see the same environment over the course of the computation. So, you know, here we have some photon that's created and like immediately flies and is, you know, measured out. Whereas this one is going to go and kind of sit in some delay line, and then it's going to go and get measured. So what we're doing by, you know, introducing some, we've kind of introduced some asymmetry into the system. So we started out, you know, intrinsically, there was no asymmetry here. Like we were just thinking about some 3D structure where every dimension was identical. But now we've sort of embedded that into some system. We've introduced time as a way of reusing resources. And that's introduced some asymmetry into the errors where maybe some qubits are going to see more errors than others. And so we can go back to our syndrome graph and look at the effect of that, which is basically going to be that, you know, some errors in certain directions might be have a higher probability of happening than others. And so, you know, you can have this idea of, you know, assigning probabilities to these edges that are accounting for the fact that, you know, in some locations, some things might be more likely than others. And there's all sorts of other different things that can happen to the errors that might take you further away from this model when you start to dig into the way the errors really behave. So, you know, you might have this kind of like spatial asymmetry, or you might have, you know, some errors that occur from different physical sources having very different probabilities, and they might belong in different places. And you can have you can also have a bias in the errors where, you know, certain types are much more likely than others. And so this is also really just a whole field of research on trying to understand how that structure of the errors is something that you can use to do, you know, to design better codes or to do better decoding, and how you want to arrange those things in the best possible way so that you can tolerate as many of the physical error sources as possible. So, you know, there's really this, when you're building up to this syndrome graph, there's some sort of, you know, physical errors that are caused by your devices. You define some architecture, and that transforms those errors into into, you know, errors on the syndrome graph. So errors at the level of the code. And this transformation is not always going to have the same effect on the errors. And if I design a better architecture, then these errors will be smaller, even with the same input. And if I design, you know, a very bad architecture, then I'll have errors that blow up or like spread around or do something bad. And this is really, where the quantum architecture sits. It's how are you mapping from these physical primitives to build up to a fault tolerant channel in a way that is as good as possible. And there's one other talk, maybe I'll point out, that's happening later this week that Ben Brown is giving, which is an idea that is of that kind. So if I know something particular about the way my errors behave, how can I exploit that to design my code in a certain way where it does much better for the actual errors that I have? So that's another good one that kind of fits into this context. Okay, yeah, so maybe, how long do we have? 15 minutes left. So yeah, maybe we can just take a couple of questions and then I'll.
Yeah, so there were several questions about the crosstalk errors. So I think the questions are like, if this architecture is robust against such crosstalk errors, and secondly, how much crosstalks are an issue, like physically in this photonic architecture. So could you comment on that?
Yeah, so I guess the model that I'm presenting is still one step removed from reality, and I'm still talking very much about it. One of the, and I kind of didn't spend really any time talking about some of the motivations for this, but one of the motivations of this kind of architecture is, and with photonics, is photons don't interact with each other. Like we can't do gates, as we talked about, and that's because photons do not interact, and so there is no quantum crosstalk. So you can for sure have classical kinds of things going on as you would in any kind of computer, but at a quantum level, there is no emergence of correlations that you don't expect, because all correlations are mediated through your interpretation of classical information and processing. And you can kind of see what is happening here, where you have a whole series of completely separate entangled states, and then you do, entanglement on them. And so there, of course, can be correlations in the structure of the entanglement that you're creating, but that is going to be limited to, the structure of the states themselves. So the correlations will be limited inside those kind of entangled. Of course, really, this whole procedure that I'm describing, of course, doesn't need to be photons. Like I'm using photons as you could build entangled states and do fusions on them with another kind of hardware, and then crosstalk could be something. And I'm afraid I'm not the best person to talk to that, because it's something which is so tied to the specifics of the physical system. And in terms of the syndrome graph, in terms of the syndrome graph, crosstalk is something that could turn up in many different ways and could really break the fact that you have a graph structure at all. So if you have some kind of physical event that's causing many things to happen in many different locations, that can be something that breaks locality and that doesn't cause only two syndromes to occur. It might cause like a whole bunch of stuff all over the place. So yeah, those are the kinds of things that when you really want to go through this process, you have to understand like what is everything that can really go wrong, and what are the bad things that can happen, and how can I design an architecture that's going to mitigate those things? That's a great question. Thanks. Okay, so maybe I'll go on and kind of wrap up, and then I think there'll be kind of plenty of time for more questions at the end. So yeah, we've been through this whole story, right? We started with photons and how we can encode them as qubits. I took our primitives, this resource state generation and entangling measurements. We can see that we can assemble those things into this fault tolerant channel. We can get a syndrome graph out of that, so we can use standard decoding techniques. And then, eventually that takes us to these logical gates. I just want to make a quick aside on this. So almost not related to the rest of the topic, but just about it's kind of strange when you take a step back and think about that whole system and what is going on, which is that photons don't interact. They're zero Hamiltonian. And yet what we've got at the end is some very complex topological system that has, all these properties of, what is essentially a kind of condensed matter topological system. And, You know, the photons are kind of an extreme case of that because they really don't interact. But actually, even with you know, other kinds of qubits, superconducting qubits or trapped ions, it's still the case that the way you're getting there by physical interactions directly between the qubits. It's by mediated, like applied projective measurements, which is classical information that you can then interpret. So, you know, there's something very interesting about the system, which is that we're simulating a topological system, which has, you know, simulating the behavior of some Hamiltonian in a way that it is, you know, really mediated by our classical processing and our interpretation of the measurement information. And so, yeah, I don't know, this is kind of an interesting connect to the very beginning, back to, you know, like where these things really came from, which was inspired by these, you know, physical systems. But now we're simulating them in a setting where we're no longer, you know, because it's simulated and because you can maybe connect things in different ways, you're actually not constrained by any of these, you know, things which would apply to a real system. So locality is no longer a constraint, and we can imagine modifying these codes in such a way that introduces, you know, things that break locality, that connect things up in different ways, or maybe they go into higher dimensions, into kind of states that you could never have relating to a physical Hamiltonian. So I know that's just to draw some kind of a connection back to, you know, this the very beginning and the more theoretical end of where we started out. Okay, so we have about 10 minutes left. And I wanted to give another example. So I went that last one in a lot of detail to show how we take primitives and combine them to get to this fault-tolerant channel. And someone had asked, like, can you do this for any kind of qubit? And I think the answer, if you have a universal gate set, is yes. And this example of the superconducting qubits is to kind of contrast and see what is different and what is the same when we look at a very different set of physical primitives. And the primitives here are the things that, you know, you will recognize as kind of circuit operations. So we can now have these 2-qubit entangling gates, single qubit unitaries and measurements. And I've just taken this example of how you can assemble those things into a quantum architecture from this paper by Austin Fowler and others on kind of surface codes and how you can construct those with this physical system. And here the idea is, you know, now we kind of have a much clearer picture of the code. So you can arrange qubits into a code, and then you can assemble these actual basic operations, so 2-body entangling operations, into some small circuit that's going to make a 4-body projective measurements to measure those parity checks, to measure the stabilizers of that code. And, you know, then by repeating this step over many time steps, you build up the kind of an equivalent set of measurement information that is going to correspond to this same fault tolerant channel or a very similar one. And so, yeah, the way of arriving here is very different, and I'm not going to go in the same level of detail through this, but you can see that you arrive at a 3-dimensional object, which is also a whole bunch of measurement information. Like ultimately what belongs in this region is the measurement information that you get along the way as you go through this process. And what you get out of the end is a code. You know, I put in a code, I get out a code at some different point in time. And in the middle, we've kind of got these measurements with a particular correlation structure that then is corresponding to our fault tolerant channel. And okay, so without kind of going through the process here, but if you analyze errors in this system, like the procedures, the way the errors happen are going to be very, very different. So, you know, now the kind of thing we need to worry about is every one of these gates that I implement can have some error associated with it. So no gate is going to be perfect. They all could introduce some kind of an error. And so what if I have some error that happens at some point early on in the circuit? Then, you know, there's some risk that those things can, you know, gets spread around to different places over the course of that operation. And so, you know, the emergence of these things is very different, but you can do a kind of similar analysis where you want to identify everything that can go wrong and track its behavior and figure out how it's going to affect your parity checks. And again, this is an example I've taken from another paper that did a detailed analysis of all of those errors. What are all the things that can go wrong? But the upshot of all of that is that you end up with a syndrome graph that looks very similar to the one that we had before. So there is actually a slight difference here, I think, and I think I've interpreted this correctly. So, but we have, you know, diagonal edges. So we have all our square edges, and they look the same. In this case, these correspond to sort of errors on the measurements. These correspond to, you know, Pauli errors on the qubits. And then there are these diagonal edges that sort of correspond to errors that got spread around over the course of the circuit. And so, I mean, it's kind of interesting to look at this example and see that, you know, the same features are there, even though the physics of the system that we're starting with and maybe the physical origins of those errors are completely different. And so this is the, you know, having looked at those two things, it's sort of, this is the end point. And I said at the beginning, like one of the big reasons and valuable things about digging into this quantum architecture and understanding these kind of more intricate details of the way things are actually behaving is so that you can take that back and use it to inform the theory that is underlying this stuff. So, you know, then you can have a better theory, design better architectures and so on. And these diagonal edges, this is like one example of one of these things that we can learn. And we saw it appears in these two different, like completely different systems. So, you know, circuit-based and superconducting qubits, you get these edges in this fusion-based picture. With photons, you also get these diagonal edges. And I think, you know, one way of interpreting what is happening here is that we're always building a system where we're starting with, you know, small entangling operations. So things that are entangling two qubits together. So in one case, it was like 2 qubit gates. In another case, it was 2 qubit measurements. And, you know, in this sort of target ideal fault tolerant channel that we were trying to build, there's sort of all these 4-body operations. So our stabilizers with these 4-body things, all these squares are like 4-body things. And as you try and build up those things from smaller operations, you end up, it's just like, this isn't something that is physically possible. And as you try and build it up, you end up having to divide up this structure in a bit of a different way. So anyway, this is some kind of unavoidable feature of whenever your primitives have a certain structure, you're always going to add these additional operations, which are sort of representing the things that happen while you are building up the entanglement. Okay, good. So, I mean, this is basically the end. We have a couple minutes left. And so I think, you know, the summary is, this is just the same picture that I had right at the beginning, is that this is a topic which just spans this very wide breadth from like these very theoretical underlying theories that are kind of governing the behavior of topological systems, all the way through to, you know, how am I actually manufacturing devices? How am I putting them into a system, and how do they interact with each other? And the kind of exciting thing, in my opinion, about quantum architecture is that it sits in the middle of all of these things, and you have to look in both directions to really get to a good conclusion. It's a way of tying together, you know, the very physicsy details that get into, you know, how something really behaves. That can then inform like all the way back to, well, which, you know, underlying theories or principles should I be looking to improve the way this thing is really going to behave. And you know, I think we're at a point in history where quantum technologies are starting to become a reality, and this is no longer, you know, purely a theoretical exercise. And, you know, maybe there will become a point in the future when this is a pure engineering problem. But right now, it's absolutely at the intersection where you need to have all these aspects tying together to be able to make progress to where we want to get to, which is ultimately being able to build a quantum computer that will run useful quantum algorithms. So there's a ton of exciting stuff going on. I thought I'd just close by mentioning a few of the interesting open problems that I think are out there. And there are many, many of them. But just to give you a sense of some of the kind of exciting directions at the moment, I think, one of those we've seen is that we really need to understand the structure of the errors to really understand how it's going to behave. And there's a kind of a combined problem here of linking up, well, how well does a decoder do? How does that classical processing work with the structure of the errors themselves? And so, I mean, you can think about improving these algorithms to do better. And I think there's a lot of exciting things there, like using techniques from machine learning is something a lot of people are doing, but also about taking that back to your system and understanding what are the right kind of errors and how can I engineer those errors in a way that like links all the way through to your understanding of the topological code. And then, there's things about this connectivity, and I kind of alluded to this, and I've talked purely about these three-dimensional systems that are based on 2D topological codes. But this really isn't constraining, and particularly with photons, you can really physically build things that have, very different structures and geometries. And so that's something which I think is really not been pushed anywhere and close to how far it can go, which is looking at codes that have non-Euclidean geometries or can't be embedded into this 3D space, looking at LDPC codes, which completely break this topological picture entirely. And there's work going on in codes that are inspired by things from ADS CFT, but actually then can turn into schemes which you might actually practically implement. So again, these connections keep going between these theoretical models and then turning these into real schemes, which might actually be able to be used. And then finally, this is sort of the wild card one, which is everything I've talked about from the very beginning, and every example that people think about implementing in practice is based on qubits. So how do you encode something as a qubit, and how do you manipulate it? And the reason for that is that, anytime you're basing something on stabilizer fault tolerance, we have this amazing framework that will tell you how to understand what is going on in a qubit picture. Or maybe QDITs would also work. But in many cases, and photons is an example, photons are not qubits, right? They're not at all qubits, and you can kind of trick them into behaving like qubits, and that gives us a way of getting a handle on what's going on. And there is just no framework to get a kind of a more fundamental grasp on how we might interact with those systems to do fault tolerance in a way which is better and more native to the systems that we're using. And I think those questions probably extend into other directions as well. So that's a kind of very open-ended one, but fault tolerance gets better by getting closer and closer to matching the operations that you can really do. And so the further you can push things in that direction, then the better we can hope these things will perform. And that is all I have. And I think there's now going to be time for questions. So Kyung Yu, if you have some to read out.
Yeah, right. So yeah, thank you so much, Naomi. It was a really great tutorial. So there were many questions, but let me just pick up one that was brought up in the middle of the talk. So when you build up this large entangled structure, like this large 3D structure, like how does the success probability scale as a function of the architecture size? Does it like decrease exponentially, or is it not, and therefore is practical?
Okay, so I'm understanding that this is talking about photons, which have these probabilistic measurements. So
yes, that's correct. Yes.
The probabilistic nature of those measurements is something that you can just interpret as another source of error. So there's lots of things that can go wrong. You're your gates might have errors, or your measurements, you know, in a circuit-based model might, you know, get flipped, or you might sometimes not get the answers back at all. And the fact that those linear optical operations are probabilistic is something that can be, you know, we can just interpret it as another source of error. And so you need that amount to be below some threshold. But once it's below threshold, then it just gets wrapped up into all of the other things, and it is exponentially suppressed. So the success probability of creating the state is a function of the code distance. And if you have a very large state, you will be guaranteed with 100% probability to create a state as long as those things are below the fault tolerance threshold.
All right, that makes sense. So I think with that, we should conclude here. So yeah, I want to, on behalf of everyone, I want to thank you so much, Naomi, for this amazing tutorial. And this was the final talk of the day, and we'll return tomorrow morning in Central European time. So I also want to remind everyone that right after this, there's going to be a roundtable session. You can join that by clicking the bottom left box on this website. So I look forward to see everyone there, and thanks so much, Naomi.
Awesome. Thanks very much.